ฮัลโหลฮัลโหลอันนี้มันไม่ค่อยติดฮัลโหลอันนี้ดีกว่า
ได้ไม่จะเริ่มไหมคะ Hi Ceiling Hi Ceiling Can you hear me
Yes, yes, I can hear clear.
you hear clearly Hi
Yes, hi.
Okay where is Mancho He is going to join our meeting
Yes, I think so. Now, I will check with him.
Yeah okay No problem We can wait himไม่นานไปหันกล้องหันไปเราจะไม่เห็นบุคคลที่พูดนะเดี๋ยวจะแค่แบบเราขอเอาแล้วเห็นอยู่
So, sorry. So I think he is in, because today he is in travel. So I think he will join a little bit later. I think he had some problem with connection. So how about so I give the talk firstly.
It's no problem. Hi. My name is Somjai, and then we would like to introduce you a bit to audience for this section. So you are the research professor at the SARI, and also you are now in the deputy general manager at the Shanghai Apatron Particle Equipment, and also you are still in the vice chairman of the ion radiotherapy branch of the National Medical Device Industrial Association. From 2011 to 2016, yes, you work at the National Institute of Radiological Science in Japan and conducting the research in CIRT, medical physics. Since 2016, has served as the chief engineer of the treatment system for the Shanghai Proton Therapy Facility, which is a supported project by the Ministry of Science and Shanghai government. So from now you can give your talk. So you can talk. Oh, Manjo also come now. So you gonna start first, or Manjo gonna start first?
I think Manzhou will give the talk firstly.
Okay. I'm
Oh, you
sorry.
can introduce yourself now, Manjo. Sorry.
Okay. I'm sorry. I make a I forgot the meeting number. So first I shall introduce of me. I'm the chief engineer of Aptron particle equipment company. So and also I'm a researcher of Shanghai Advanced Research Institute of the CAS, and uh, I have uh, uh, I have do several the accelerator physics design of the SAPT project. So my my talk is about uh, accelerator of the particle the proton project of the SAPT. So can you see the slides?
From online now, yeah, we can see it, but it's not full screen. It's full screen now. Yes.
Okay. So I should introduce several of the Shanghai Advanced Proton Therapy, and I shall introduce several technology and developing in the Aptron and SSRF. Shanghai Proton Therapy is a dedicated proton therapy. So it is funded by Shanghai local government and also the Ministry of Science and Technology of China. No, this proton therapy is developed by Sari that's a spin-off of the Shanghai light source and installed it in the proton therapy center of Shanghai Region Hospital. There are three initial treatment pipelines. So
So sorry,
it
Manjo is this.
okay.
I interrupt you for a while. So because some people are online, so cannot see that your slide is not updating.
Oh,
Just a few
uh,
minutes.
okay, okay. I share it again.
Can you? Oh, you're gonna share it again. Thank you.
I share it again. I will try. Okay. Can you see the slides?
Yes, yes. Could you please to make it full screen? Yep.
Okay, okay,
Thank you.
okay,
Yes, go ahead. Yep.
okay. So this project started in early 2014, and this is a picture of Surrey, Shanghai Advanced Research Institute, and this this one is the Shanghai light source, Xingshou light source, and also we have another institute called the Shanghai Institute of Nuclear Institute of Applied Physics. That's in another district. This is the building of the region hospital. Uh, uh, this is the building of the proton center. And also, this is the layout of in this building. We have proton selfie in this area. Okay, and we have also other utilities such as power supply and cooling water, and power station, and so on in the other building. And in this Proton Center, there also have nuclear medicine area, and also LINAC photon facility in this area. Yes. So this is the milestones of our project. It started very early in 2012, and we finished the accelerator installation, and the commissioning started from 2017. And also in the next year we installed the gantry, and also have several third-party testing. And in the last year, we in the 2012 we have finished the clinical trial, and then get the registration of the China government, and then is open to the clinical treatment. Uh, this one shows the proton facility, the layout. The accelerator is here. We have a 7 MeV LINAC. It consists of RFQ LINAC and DTL LINAC, and then the low energy transport line transported the beam to the synchrotron. This synchrotron accelerated the beam from 7 MeV to 70 MeV, or even up to 235 MeV, according to the treatment requirement. And then here is the high energy transport line. Then the transport line send the proton beam to different treatment rooms. So here is the eye treatment room. So the beam energy is fixed to 75 MeV, and and this is a fixed beam room. The beam direction of the is 270 degree, and this is a couch. And then we have two gantry beam line. Gantry here is a half gantry, 180 degree, and here is a full gantry. It can rotate it a circle, fulfill the 360 degree. And this is the main parameters of this machine. We have 94 energy. We can supply 94 energy proton beam, and the beam intensity per speed is around 4 10 to 10, and the accelerator is a synchrotron. It uses a very simple photo structure. It means focus, drift, and defocus, and drift, and the circumference of the ring is about 24 meters. We use multi-turn painting injection to cause higher beam intensity, and the extraction is used third resonance slow extraction because the treatment require a long time and nearly DC current. So the the beam needs point 0.7 seconds to accelerated from 7 MeV to 70 or 235 MeV. And the extraction extraction time can be variable. So the repetition rate of this machine can be variable. So we use spot scanning beam delivery. So this part maybe Zhiling will give more introduction of the treatment part. So my topic mainly focus on the accelerator, and the treatment I will skip the slides. So the synchrotron. This is the design of the synchrotron. The yellow one is the dipole. We have 8 dipole, and the blue one is the defocusing quadrupole, and the red one the focusing quadrupole. So there are 6 and 6 QD and QF, and this one is the lattice the twist parameters, the beta function and the dispersion. We have a lot of optimize to suppress to reduce the beta function, and to make much more acceptance of the proton beam to in order to get much more higher beam intensity. And here is several parameters of the synchrotron. So this is the tube, the work point as injection and extraction, and the max beta function is nearly about 6 meter. So, and the transition gamma is 1.5, and below the the ramping process, the energy is below the transition energy. And also this slide shows the injection progress and the extraction. So because the current of the Linux is not so high, we need use multi-turn injection to store much more beam intensity. So we use a painting. This called a painting. In this progress, the beam bump of the stop beam decrease in horizontal beam space space, and also have several mismatch in the vertical phase space. So, but the injection efficiency of the multi-turn injection is not so high. It's only about 70 or to 50%, but it can use very or many turns, so the equivalence turns of about 10 turn, and also this shows the third order extraction phase space. So we use half-kick out method to make the stop beam the emittance of the star beam to span and then exceed the stable region to the unstable region. This one shows the base space. There are three separates, and then we put electron septum here, and it bends the the beam out of the space, and then uh, transport from several dipole and quadrupole, and then enter the the magnetic septum, and then go out from the ring to the transport line. And this is several components of the accelerator. Here is the oh sorry. Here is the dipole magnet. The magnetic field is up to 1.7 Tesla, and this is quadrupole and sextuple, and this is a type of the extraction electric septum. The stop beam goes through here, and this is a very thin pole, very thin uh, slice, and then the extraction beam goes through from the gap of uh, these two components. And this one is the RF cavity. The RF cavity, the voltage of the cavity is not so high. It's only 2 kilowatts, and the frequency of the RF system is changing from injection to the extraction. This is the power supply of the main dipole. It's 1,200 amperes, and the power is very large of this power supply. This is the picture of the whole machine. The the Linux installed here, and this is the synchrotron, and then this is the high energy transport line, and also this transport line send the proton beam into the treatment room. In the operation of this is 3 or 4 years, the reliability is very good of the proton accelerator. The uptime is much more than 98% in the clinical trials. This is several commissioning results of the during the commissioning. So we got the first beam of the injector just after 1 week installation, and also we got ramping of the beam just a week after the first beam, and then a week we have the first extraction beam at the profile of the high energy transport line. This shows the extraction beam, and then we have tuned 94 energies, and we have several rotating beam. This picture shows the beam signal in the Faraday cap in the energy line, the green one, and the blue one is the beam current in the ring. So we can see the current in the ring decrease, and the beam current in the high energy transport line keep constant. Then also we have several optimize to reduce the beam spec, and to reduce the cut off time of the spot scan. And also we have several experiments to try the multi-energy extraction, which means we can extraction several energy in the one spill to make more efficiency of the treatment. So the treatment system, Zhilin will give some introduction. So I just skip the treatment system. This is the half gantry 160 and 80-degree gantry. This is uh, uh, 13 13 meters long, and it's 11 meters in radius, and the total weight of the country is about 170 tons, and the rotating part is less than 100 tons. In this picture, the white part is fixed, and the blue part, and also the transport line is can be rotated. Also, we have another gantry, a full gantry, and then the gantry is much smaller than the 180 tap. We reduce the length, and also use combined function depot to reduce the weight of the depot. Also, this is several beam parameters. We have marriage in during the commissioning. This is the beam position in the gantry is less than 1 millimeter. And also daily QA results, and also I can introduce several technology during under development, such as we should reduce the size of the proton selfie, and proton CT, and also flash. This is we use superconducting magnets to make the synchrotron and the gantry, and the gantry weight can be reduced to less than 30 tons, and the size is less than 6 meters, like that. And also have several try to use the full Linux, also can be used for Flash, and also we can do the use the Proton CT to reduce the range uncertainty. And also the Flash, we have several design of the fast cycling of the synchrotron, and then we can use the layer staking method to do the beam delivery system, and then we have designed several experiment platform for the biology effects to make more understanding of the flash system. So also we have several design for the multi iron selfie, and this is my talk about the accelerator part. Okay.
Well done. Yeah, thank you for your presentations. And now, so, we're gonna go for questions. Who can, so somebody can ask some questions.
I'm Dr. Ravi. Thank you for your excellent talk. My question is, do you plan or have able to do for the dynamic arc proton in the future?
You mean the arc technology? Maybe Zhiling will give some answer of the arc. We have several primary study of the arc, but not very very more very much design of the arc system, because you know the synchrotron, that's a pulsed beam, not like the cyclotron. So how to synchrotron how to make the beam and the rotation of the gantry, how to make their at their movement at the same time is a question, and we need more study of that.
You are starting to investigating on the proton arc therapy, right?
Just very little research that, not very much. Yeah.
Thank you. Can I have question? I'm the medical physicist at Lama Tipiti Hospital. Do you plan to do the gating with your proton system?
You mean getting we have the interface, and also we do the gating in our clinical trial. Yes, we have the gating technology now.
So your system can do the gating, right? I cannot
Yes.
catch up
Yes.
your. Oh, and
Yes.
how long the beam can hold? How long the beam can hold when the
Yeah.
patient restful?
Actually, during the gating, we turn off the beam and ramping the beam again during the off time, and so the beam
Yes.
and also we can hold the beam. Also we can hold the beam. If we hold the beam, the time is more than 10 seconds. So we have
Sorry,
two modes.
how long?
We have two modes to deal with the gating.
Huh?
One mode is we don't hold the beam. We ramp down the beam and then injection again during the off time. And then if the requirement of the beam turn on, we can turn on the beam um, in very short time. And the other mode is we hold the beam in the same energy, don't ramp up. Don't ramp down, don't ramp down the beam. So in this mode, uh, the mode most of the wait time is 10 seconds.
And how long can the beam can ramp up or start again?
Yeah, the start of the beam is less than 10 milliseconds. Less than 10.
10 millisecond?
Yeah.
Thank you.
Hello. I have a question about the transportation efficiency from booster to different room. Do you have any idea about that?
The transfer efficiency to the different treatment is very high, is much more larger than 95%.
To all clinical rooms, they are all the same, 99%.
Yes. This from the extraction of the synchrotron to the different room, but the extraction efficiency not so high, maybe 80 or to 90%. So the transmission efficiency the beam lost mainly in two uh, process. One is the ramping, and the other is the extraction. And if the beam is extraction from the synchrotron, the transition efficiency in the transport line is very high.
Thank you.
So, hi Manjo. Can I ask you one questions? So in your clinical trial, so I saw that you are you can ramp the energy from 70 to 235 MeV, and how about 250 MeV for the machine? Can we reach at 250 MeV or not? Have you ever tried during the commissioning to meet that energy for
Pardon? You mean we can extraction 94 energy? We have 94 energy in the
is a
extraction beam we have.
specification of the machine?
Yeah.
Sorry, I interrupt you. Sorry. It's in the
Uh,
specification of the machine that is 250 MeV for proton energy, right? And then for
yeah.
the clinical trials that you vary the energy range down to 70
Yeah. You
up
mean
to
the
235
maximum
MeV.
energy? Yeah, you mean the maximum energy of the synchrotron. So the design of the
Now it's
synchrotron is
235.
is 235. Uh,
Uh-huh.
the design of the synchrotron is 250, and we found we don't need so high energy in the clinical use. So the finally we supply the max energy is 235.
So, and also for your design, the RF carrier can handle up to serve for 250 MeV anyway, right?
Yes.
And so, thank you. And another question. So I saw that you use a slow extraction with IFKO. So, how about the switching time or when we switch the beam deliver room to another room, how fast it is when you use the slow
Uh,
extraction IFKO?
Actually, we don't change the beam to one from one beam one treatment room to another room in one spill. We don't change the room in one spill. We change the beam room during the off time. You know, so the FQ and the change room is not the same not in same thing. If
And
the
okay, okay.
if the switch room the progress of a switch room uh, occurs in the progress occurs when the synchrotron is off. There is no beam in the synchrotron. If we
Okay. And how long you gonna take
change room.
for the beam on again? How long it
The
takes for
beam
beam
on,
on again after beam off?
it's very quick. Is if there is no beam, it may take 1 or 2 seconds to ramp up, and the beam
To
is
ram
off.
up.
Yeah. If
Okay.
the beam
Thank you.
is keeping, so the beam on time is less than 1 microsecond, 1 millisecond, 1 millisecond.
Okay, thank you. And another question
Okay.
from
Excuse me, may I ask you about the injector? I mean the ion source at the beginning. What kind of the type of the ion source you use right now?
Yeah, right now the iron source is dual iron source, and we
What is?
wanted to we
Can you say it
wanted
again? Sorry.
to update we wanted to update the iron source to ECR iron source.
All right. So you mean right now it's not ECR yet, but you have planned to make it
Yeah,
into the ECR, yeah, right?
Yes.
what
And what's kind of the current ion source?
The just a moment. The iron source of now is what's the source of the is let's is dual ion source. The DUAL.
A-O-N. All right, maybe we can ask later.
When are you going to upgrade to EC ion source? Is it soon or next year or maybe later? Do you hear me?
Yeah. In the next machine, we use ECR light source.
When are you?
Yeah.
You do not know yet?
We change the iron source in the next machine because this machine we can't change because the how to say the law
Regulation.
the equipment, yeah.
Actually, currently the machine works quite well. And also the injector actually works well. So we are not going to change the ion source in current machine in Beijing Hospital. But for the next one, we will use ECR ion source as Manzhou said, because it's easier to maintain, to operate.
Can you explain a little bit more what is the advantage of the ECR compared to the current one? Why is it better and in what aspect?
Because this one we have the filament in the iron source, so we should change the filament 1 year once. So if we use the ECR type, we don't need that.
Okay, thank you.
For the synchrotron, can you extract the energy in the single energy or the multi energy extraction?
Yeah. Because now the way extraction the beam in single energy, so the ramping up time and ramp down time makes it not so efficiency. So we want to update to multi energy because the treatment don't need so large particle number.
So is that the single or multi energy extraction? Is that single energy extraction? Your synchrotron?
Yeah, we extraction one energy and then ramp down the beam to the other energy and then extraction again. This means multi-energy extraction. And then in now stage we just ramp up the time and extraction the beam at 1 energy and then ramp down to 0 and injection again. So the ramp up time and the ramp down time may take more than 1.5 or 2 seconds. If we ramp down from 1 energy to the other energy, this only take maybe 0.2 seconds. we can reduce much more time.
Okay, thank you very much. So could I
Yeah.
pass to the next speakers and to Chiling? So could you please to share your screen?
Yeah, okay.
Thank you.
Just wait a moment. I'm
Yes.
trying to share this. Moment. Okay, can you see my screen?
Okay, yes, we can see your slide now. So
Okay, thank you very much. Thank you very much.
can you can start now. Thank you.
Yeah. So thank you very much to give us this opportunity to introduce our proton therapy system. Manjo has already give you an overview of our system, especially the accelerator system. Talk we'll focus on the treatment part of the machine. So I believe you already know the proton therapy very well. So I'm going to skip next slides. It's about so in China there are lots of cancer patients need radiotherapy, and proton therapy now is in China, there are more and more proton centers and commissioning and construction in China. So as you know, the advantage comes from the Bragg peak. So there are many advantages in clinical for proton therapy. For example, the less toxicity and the more efficient treatment, especially good for children. And maybe for immunotherapy, proton therapy also can work well with it. So there are more and more patients, more and more hospitals. They are they favor proton therapy. Now more and more centers in worldwide, especially in United States and in Japan, in Europe. So Manjo has already given you a overview about our system. So in Beijing Hospital, this system actually is kind of a prototype for of our first machine. So the system consists of injector and synchrotron. The beam, so the accelerator accelerates the beam to 70 to 235 MeV, and there's a distribution transportation line can distribute the beams to different treatment rooms. Currently, our center has 4 treatment rooms. In the middle of these 2 treatment rooms, horizontal beam line and the half rotational gantry beam line these two rooms has already get Chinese FDA clearance. Since last year, those two rooms treat patients every day. And there are another two treatment rooms. One is eye treatment room, another one is for rotational gantry room. So these two rooms are under commissioning, and we expect this new gantry room will be available for clinical in this year. This is the layout of the Beijing Proton Center. You may see the main part of this is the underground floor layout. So the proton therapy machine itself is occupied about 5,400 square meters. So because in the beginning of the development of the machine, actually we don't know what's exactly the size of the machine. So actually each room, including accelerator room and also gantry room, it's larger than we really actually need. So that so means for next centers, it will be smaller than this one, because when we develop the first machine, we always want to leave some room for the development. And actually, Manjo has mentioned, so this accelerator is a spin-off of the SSRF in Shanghai. It's a synchrotron radiation facility for basic research. So scientists, engineers, based on the technology they already have, they developed this proton therapy machine for Beijing Hospital. So this proton synchrotron is the first one in China, and also it started the operation in 2017. The synchrotron, maybe you know there are two kinds of accelerator now widely used for proton therapy, including cyclotron and synchrotron. For synchrotron, you may see from this image, it's somehow larger. The diameter is larger than the cyclotron, but because the synchrotron can change energy as the need according to the needs of treatment. So it's not net. So the synchrotron system do not need a degrader. So it's cleaner compared to cyclotron. Cyclotron usually need a very complicated energy degrader to decrease the energy from the accelerator, and so usually they lost most of the beam, especially for the lower energy. For example, for 40 MeV, usually cyclotron lost more than 99% of beams. So it means there are lots of activation due to the loss of protons. But for synchrotron, you don't need a degrader. So this system is cleaner. For example, if we switch the beam, the operator, they can enter this accelerator hall immediately after we switch off the beam. But for cyclotron, it's very difficult because you always need hours to wait the cool down of the machine. So this means the system is more energy efficient. For example, our electricity cost is about less than 1/3 or 1/4 of IBA IBA cyclotron. The old IBA cyclotron used for multiple treatment rooms, and this means we can reduce the radiation shielding or thickness, and also it's much easier to maintenance and provides high availability, and finally the machine has to be decommissioning after maybe 20 years or 30 years, because cyclotron is very dirty, so you cannot just throw away. But for synchrotron, it's much easier and much cheaper to decommissioning. And those data actually we measured in 2018. So Manzhou, he was responsible for the design and the commissioning of the machine. So our overall accelerated performance is quite good. The beam stability and repeatability meets the design requirements. It's a startup and within the whole running day. And the beam position and support size repeatability is better than 0.3 millimeters, on par with Hitachi or other synchrotron. And the beam position stability is within the in one spill. Even in one spill, the beam position may be changed because of the extraction. So we can keep the support position in less than 0.2 millimeters, and we can switch off the beam in less than 0.1 millimeters microsecond. So generally, our proton accelerator performance is really good, and the operation was really stable and reliable in past several years. The overall availability is about 98%, and the MTTR means how how long when we need to repair the machine is less than half hours. So most of faults recovered in 10 minutes or even less. So we use pencil beam scanning, as you know. So now most of proton therapy system use pencil beam scanning now, but actually 12 years ago when we started the design of the machine, it's not clear for us which way we should go. Fortunately, we choose the correct path, and we developed this high performance pencil beam scanning system, and the beam support size is about 0.3 millimeters to 7 millimeters. And the scanning speed is about 2 centimeters per millisecond. And the rotation, we have rotation gantry for high performance IMPT treatment. And currently, because the whole system developed by ourselves, including ionization chamber and scanning magnets, scanning power supply. Currently, we already export. I mean, in Europe centers already selected our ionization chamber monitors for their upgrades. We already export more than 10 ionization chambers to Europe. On these slides, you can see you may see the IDD curves and support sites in ISO centers, and also the dose distribution with PTW matrix ionization chambers. So it shows very good performance and stability. So this slide shows several first scanned image we got in 2017. And the very earlier image you see, most of the first image we got from screen and the from links, IBA links. You see it's a little bit, it's not so perfect, and but later we can do very good scanning beams, and this is the first Bragg peak measurements we got in water fountain, and these are some earliest scanning images we got, like the flowers. This is the city flowers of Shanghai, and also the scanning pattern matrix of matrix. And those systems are developed by ourselves. For example, this treatment nozzle, you see the ionization chamber, and also you cannot see here, but behind this moving floors, there are scanning magnets and scanning connected to the scanning power supply. So it works very well during last 5 years. And this is the first gantry, also the first gantry in China. So the weight is only 96 tons, and the accuracy is better than 1 millimeters. So this is the 2 treatment rooms we already hand over to the hospital. They have already treated many patients, and now treat every room treat maybe 20 patients per day. And so in this gantry room, at that time we selected this open design and half rotational gantry. And it's convenient for positioning and operation, and also it's cooperated with 6-dimensional treatment couch, provide necessary treatment angles, and also some of you, I think you have just asked Manzhou about the gating system. Actually, our system already integrated gating system based on an amplitude of motion of the target area to track the tumor location, can achieve very good precision treatment. So this is a 2 imaging panel can be used to take the image of the patient, and can be used to for patient positioning and also and gating. You may see this camera. This camera is used to track the surface of the patient surface used for gating. There are some tests we did for Chinese FDA clearance. You may see, with the so we put the film in a motion fountain, and we use when we use the gating system. This is with gating system and without gating system here. So you can see with our gating system as can effectively mitigate the motion for the treatment. And our system shows good reliability. So for example, for the clinical trial of half a year, so every day we run about 18 hours per day, because at that time we treat patients in the daytime and also do the commissioning another room in the night time. So we run the machine 18 hours per day, and the availability is quite good. And also the overall system, the performance of the system is on par with the Hitachi machine. which now is running in Mayo clinics and other centers. And we took this image, take this video, actually in 2021, and for the workflow test, you can see the operator operates the robotic coach and the gantry, and do the patient positioning, and push the treatment plan to the irradiation system, started the irradiation. And this is, we measured hand net treatment plan in water. And this is the square, the cube plan. Okay, after we finished the commissioning, we shifted the machine to the hospital. Beijing Hospital, their clinical operation team, they did lots of tests before the clinical trial. So they did, there are two parts for physics commissioning. One is acceptance test, means they did lots of tests for beam performance, mechanical and imaging system, also safety system. They, after the acceptance test, they did lots of work for clinical commissioning, including treatment planning system commissioning, and define the QA baseline, and also define operating instructions. So these are based on the IEC standards and also AAPM reports. So they did, for a single treatment room, they did more than 258 hour tests. So this is the acceptance document I have sent for them. And after the clinical commissioning, they started the clinical trial. They treat 47 patients in less than half a year, and that was very successful. It shows a TCP of 100%, and no patient had a grade 3 or above acute toxicity. So this shows very good stability of proton therapy system. So so we got the the Chinese FDA approval right after the clinical trial. And in last year, Beijing Hospital has already treated some patients, and this is the overall. This is from my colleagues. This is overall reliability of the machine. It's about 95 to 98% for each year, each month. And in the clinical operation during last year and this year, they also did very strict QA. And during the treatment process, there are there was and the machine was quite stable. For example, you can see on the upper right of the slides, you can see this deviation of the support of the range, and also the deviation of the dose in the QA, and this is their QA threshold. For example, for patient positioning system, it's less than 1 millimeter, and for patient specific QA, so it requires 95% of gamma index pass. That's what we have already finished and already commissioned and shifted to the hospital. And there are another 2 treatment rooms actually under commissioning, and one is eye treatment room, because proton therapy is one of preferred treatment method for the tumors as ocular melanoma. And so this system is a collaboration with Switzerland, Swiss PSI Institute. So we cooperate with them. Basically, we copied their treatment nozzle and this double scattering system to for the eye treatment. And so this system is under commissioning, and we hope it will be the first eye treatment system for Chinese patient. And we already we also developed an R&D center, which is not far away from Beijing Hospital. This center has several buildings. One you can see here is R&D buildings. We have laboratories here, and this one can see this building is a dedicated building for accelerator and treatment system. We currently are build our second synchrotron here for R&D, and also in the future, the new synchrotron we delivered to the patient can be tested here, so to make sure we can shorten the commission time and the work in the user's hospital. So our system basically is a modular design, so allowing to be customized according to the specific needs of the hospital. For example, the land area, the land shape and area, and also the patient's throughput of the hospital. So this includes the flexibility to choose the number types of treatment rooms desired, as well as optimizing the overall system layout. And so in the future, we suggest the hospital can select, so this is our standard treatment room, a full rotational gantry treatment room with efficient implementation of IMPT workflow and advanced dual energy CBCT, so can for state-of-art patient positioning. And we also, our software implement AI and gating system based on the range of movement of the target area, not just the surface of the patient. It can based on the movement of the target, combined with the CBCT, provides accurate and rapid treatment. And work with the Chinese Academy of Sciences. So we are also developing some new technology with plans for their new accelerator technology to the clinical application. For example, now we are working with them to develop a high gradient linear accelerator, so which can be used in the future for real flash therapy, because flash therapy need very high current and also require to change the energy, modulate the energy in millisecond. That's what we can only do with a linear accelerator. But currently, linear accelerator is too expensive for proton therapy. Our task is to use high gradient accelerator structure, which can make it much smaller and cheaper for future proton therapy. And some of your, so you just asked my colleague about arc therapy. Actually, we already did some preliminary work on arc therapy because we so make sure we can upgrade our gantry for arc therapy in the future. So as you know, so arc therapy requires irradiation, the proton beam, and scanning the spot and switch energy layers, and it can maybe reduce the integral dose, reduce the dose to OAR. And it has the ability to optimize LET and improve the treatment efficiency and enhance robustness of the plan. So there are several tech challenges now we are working on. One is about dose calculation and optimization. So this is possible to solved by future treatment planning system and rapid energy change, because we need to change the energy during the gantry rotation. Currently, as Manzhou said, we are so we have already developed multiple energy operation in single spill, single cycle. So now we are already work on this, and I believe the second our synchrotron will have this function. And also we are working on to maintaining the beam delivery accuracy while rotating gantry. Currently, because the mechanical accuracy of our gantry is really good, so it's not so difficult for us for this. And currently, we are also optimize the synchrotron control system for arc therapy. And we hope in the next synchrotron, we can do some work and demonstration for arc therapy. And also, we have this model design, for example, 2 layers design to reduce the land occupation for the proton center. And we also have some development work with Shanghai Proton and Carbon Ion Hospital. So we developed this. This is actually a conceptual design of multiple ion system, which means we want to treat patient with different kind of ions in one fraction. And recently we have already signed the cooperation agreement with Toshiba. Maybe some of you know Toshiba is a leading company in carbon ion therapy. So we are working with them to enter the market of heavy ion therapy and to provide Toshiba technology to the Chinese hospital. So basically, we will work together and use their technology and develop the carbon ion therapy system in China. And so this is a summary. And so the demand for proton therapy in Thailand is likely driven by the increasing incidence of cancer, the growing awareness of the proton therapy as a treatment option, and the availability of the proton therapy centers in the country. So we look forward to constructively cooperation with Thailand hospital to better serve Thai patients and develop the next generation of treatment technology. We are open to cooperating closely with Thai hospitals and researchers to provide a customized solution tailored to your special needs. Our aim is to offer advanced proton therapy systems at a lower cost while improving treatment efficiency. Together, we can make cutting-edge cancer care more affordable for the people of Thailand. We welcome the opportunity to combine our expertise with your clinical experience for innovation research and drives progress in this field. Let's join force to elevate cancer treatment in both in China and Thailand.
Thank you for your presentation. So it's a question.
Very much.
Thank you very much for your presentation. I have one question. I know that Pacton is the company that is expert in accelerator. I just wonder that the system, like the image guide, like the cone beam CT, like the orthogonal X-ray, or like the gating system, do you have collaboration with the third party, or do you develop by yourself, or do you open for any vendor to come in to use for the gating system and the image guide system?
Okay. So for corporate photon therapy. So we work with them, developed our gating system for proton therapy. So currently for CBCT, so we have a team developing CBCT. So generally our like for imaging system for imaging guidance system, we are open to collaborate with third party because developed for many years. There are already lots of established technologies, and but it's not imaging guidance system work well for photon. It will automatically work well for proton, because the proton machine is more complicated and requires higher precision for operation, especially for gating. So that's why we have a team to translate some clinical requirements to our system to integrate imaging system. So basically, in short, so we will work with third-party company, but also we have a special team, so to integrate the system. And because before I work in Shanghai, I was working for QS, also for research for imaging guidance for carbons. So we understand So there are lots of difference between two proton and the proton. So we have some ideas now currently working for our new CPCT system. And also for gating system, we are open our interface for third party device. Okay.
Okay, thank you.
Thank you for your excellent talk. From the video that you show, that I see that your system is a Chinese-based language, right? So if you want to say if it come to Thailand, so you have to make it into the Thai version. Am I right? Oh, if so, sorry, English version.
Yeah, currently our interface actually is in English.
Okay.
So from from the beginning, I think our software can be easily change the language. So we have a special a special configuration which can put the translation and easily to change the language.
Okay. So in English is fine. English.
Okay. I have a question. In case maybe next year or next 2 year we install your proton system, and in the next 10 years maybe can be the synchrotron or the proton system can be upgraded to the new version of your system.
Yeah, I think actually is so technically, I think it's not so difficult to upgrade the system because it's a modular design, and for synchrotron, it's for control system and the magnets and the power supply. It's it's not so difficult to upgrade. So technically, I think it's no problem. And the second one is for regulation. So after we upgrade the machine, so what kind of regulation we should follow in Thailand? This is an open question. I think we should discuss. And for the third one is because the hospital has to run the machine for to treat patients, and the upgrade cannot be do some upgrade, significant upgrade cannot be done in the same time of treatment. It needs time to replace the hardware, upgrade software, and commission, and also commission the machine. So so this also have to maybe have to stop the machine. So so I think this is a very complicated question. So we should be aware, and but I believe for synchrotron, in next maybe 10 years, there are no much different in hardware, so we can improve the control system for better performance, like multiple energy change, faster energy change, or even improve the efficiency. But for treatment rooms, I believe there will be significant improve year by year. So maybe you can, for example, in the beginning, there are 2 treatment rooms, but we can leave another empty treatment rooms. So maybe 5 years later you have more patients, so we can install new generation treatment rooms in that place. And when you have the new treatment rooms and to treat the patient, we can upgrade the old treatment rooms. So this is maybe give you a more make the transition smoothly.
Okay, thank you. And one more question. I saw your presentation. Right now you join with the Toshiba, and in the future, is it possible you are going to, I mean, to make like the proton carbon machine? And I think if in case we are also interested in this system, we have to prepare or set it before with you now to prepare in the future, right?
Yeah. Yes. So currently, Toshiba only make carbon ion machine, and I believe they think they are also developing helium, oxygen for new ion species for the treatment. So, so this is their what they are doing. So they have no plan for proton carbon machine right now. But in China, currently we already are working with a Shanghai hospital, as I mentioned, so about this multiple ion machine. So they request we provide from proton to carbon, and maybe future also provide new ion species. So currently we are working on this, but not yet. The design is not yet finalized.
And may I have more questions? So could you please explain more about your maintenance or the engineering time? Because I saw from your slide that you only need a few hours per day for the engineering times. And could you please tell us about the whole maintenance program, that how many days that we need for the things like that?
So currently, so in Beijing Proton Center, so in the morning, usually we hand off the machine to hospital, the clinical team in 8 o'clock. So usually our staff start work in 6 in the morning. So they turn on the machine and also do the machine QA, and to make sure every energy and each specifications meet to the requirements of the hospital. Then they will give if they make sure the machine is okay, so they will give the report to the hospital and hand off the machine to the hospital, the treatment room to hospital. So usually the treatment start in the morning, 8 o'clock, and to the evening. And after that, usually the hospital needs several hours for QA, because they have lots of monthly QA, weekly QA, monthly QA, and patient-specific QA. Usually, they take several hours every day for those tasks. And in Saturday and Sunday. So Saturday, the hospital usually use half day for their clinical QA work. For example, patient-specific QA, sometimes longer. And our maintenance team usually need another half day to check the machine or to adjust the machine. For example, in the working days, maybe they found some energy is not so stable. It's acceptable, but not so good. So usually they use Saturday afternoon so more. And Sunday is usually the machine stop for maintenance and out beam or change some parts if they believe it's not so stable. So basically, that's our schedule. For the man is what you expect.
Yeah, of course. Thank you. May ask about the spare part. Normally or mostly, where are your spare part come from? Is
From the
your
Amazon
your
industry.
China only spare part when some
You mean spare part? Mm-hmm.
yeah.
So for spare parts, we have so we have lots of spare parts in the Region Hospital. So if there's something wrong, we can change the parts immediately. So far, it works really well. So we haven't missed single day during last year treatment. Actually, during last 2 years operation running, we haven't missed any single treatment day. So usually we can replace the fault parts immediately after we find out the problem. So if there is a machine in Thailand, we also have to have such not only the team, operation team there, but also we will have necessary spare parts in a place nearby the proton center.
I think what she meant is for your machine, where are the suppliers from? Are they all from Chinese company or some of them from abroad?
Okay, so currently, for accelerator, the injector is we bought from Hitachi because it's cheaper. At that time, we developed the machine, and other components are all from Chinese supplier. And for currently, we already developed injector our company. So for next machine is already under manufacture. So that one will be I think almost all important parts are made in China. But of course, there are some parts it's common.
So when you say
worldwide, so
when you said injector, you mean all components starting from the iron source up to the end of the transport line? those are from Hitachi
Yes.
or something? Okay.
Yeah, current
And you
current machine in Proton, in Region Hospital, it's from Hitachi. Next one, it will not from Hitachi because we already developed the injector, and we already so it's already running and meet the specification, design specification last year. So for next machine, it will be our own products.
So the one that, let's say, if we get one, the new one will be totally built in China.
Yes.
Okay, thank you.
I think that's today. We really thanks for your for your kindly presentation for us. So I think that for this section we will already finish, right? And thank you very much, Chi-Ling and Manjo. And we hope that we will make a collaborations next. Yes.
Thank you. Thank you very much.
Okay, thank you. See you. Bye bye.
Bye. Bye.
Breaking. Oh, yeah, I did. I take a bunch of notes seriously. Oh. I'm nominated.
แต่เปเปอร์มันไม่ได้บอกว่าquality ตอนที่มันดีสเรียนครับแต่มันจะแตกต่างกันแล้วทำไมเขาไม่จากสุดยอดเลยก็จริงๆก็คือนึกว่าเราจะทำอะไรไม่จะไปเลยเพราะว่าถ้าอย่างนั้นก็ไม่ต้องพูดอะไรก็เราทำไปดีกว่ามันก็แต่แบบเขาอยากให้เขาไม่ได้ให้ทีเดียวกับเพลง
โอเคที่ได้มีสุขภาพดีเกินแม็กซ์เมอร์อย่างเงี้ยแล้วเราก็ให้มันสไปรัลอย่างเงี้ยที่แบบไม่ได้ชนะมันไม่ใช่คือมันเชนส์เป็นสิ่งที่เราไม่ดีกับสิ่งต่อสิ่งที่เราจูนในวันที่ไม่เข้าเนี่ยก็เรื่องปกติไม่ได้เดี๋ยวได้ไม่ใช่สไตล์ไม่ใช่ไม่จะยังวันเรามีอาชีพไปต้องคนแต่วันเสียดายสับสายเป็นที่ต้องเป็นเรื่องของอะไรหลายแต่ที่เรียนอะไรก็แล้วเราทำแต่ดาวเลยแบบดาว
ก็ดีเสียเราสวินได้แล้วได้โดยหลักการที่เราคือถ้าดีสายใจหลักการ ที่ใส่ฟรีเนี่ยเราต้องบางทีเปิดแบบนี้ใช่ไหมไปกดบ้านแล้วก็ฟิกซ์มาแล้วก็จูดมาใช่ไหมจุดได้แล้วแต่หรือว่ามันเพิ่มซึ่งโดยที่แบบไม่อาจจะไม่กินในสมัครว่าออกแบบให้เขาติดงานแต่ก่อนเข้าหนึ่งเลยก็ได้หนึ่งไปเนี่ยแม่คนดีว่าไปมันจะต้องมันจะเก็บในเต็มต่อปากแต่เหมือนแบบติดที่เข้าใจเต็มของเลยตัวเนี้ยเหมือนกับบริษัทที่ถ่ายแยกของตัวเองแล้วก็มันตัดไปแยกแต่แยกเข้ามาเปลี่ยนแต่ละส่วนแต่ถ้าเนี้ยเหมือนซิสเต็มของมันเป็นเราบริษัทเนี่ยพอมันได้เป็นอย่างเช่นแล้วเราคือป่าทำไปได้ฉะนั้นไม่ต้องไม่ขออีเวนต์ที่เนี่ยไปต่อเราได้เรื่องนี้แล้วก็ต้องเก็บไม่ได้ต้องเก็บตามต้องเปลี่ยนว่ารีเฟซว่าจะทำอะไรบ้างจะว่าตอนก็ต้องตรวจแล้วก็ไม่ใช่ไหมช่วงไปอื่นเสร็จเลยต้องเราติดหน้ามันต้องไม่ติดที่เราต้องเก็บได้เลยอยากจะตาใส่ในการในแง่ของฟังก์ชันด้วยไปดูตาด้วยไปสิ่งต่างๆเวลา
Yeah, the snacks up there.
so full yeah
It's a little chocolate cake. Yeah,
ริงๆไม่ควรจะเข้ามาอย่างเงี้ยนะคนได้แต่เขาก็บอกว่าต้องดีใจต้องดีใจต้องได้แหละว่าแต่ถ้าเป็นแค่สิ่งของสิ่งเดียวที่ต้องตัวเองไม่ยากสมมติว่าเราทำประเด็นชั้นต้องสิ้นปีอ่ะถ้าไม่รู้เหมือนกันต้องไปชมบอกเองตอนจริงเองเราตามไม่มีไปตามเป็นประเด็นจริงๆเขาจะต้องตั้งบริษัทอะไรเขาก็มีบริษัทในไทยหมายความว่าที่เป็นอะไรนะด้วยที่เหลือที่บริษัทเองคนนี้คือเขาผ่านแพ้ก่อนแพ้ผ่านวันที่เป็นคนไม่ถึงว่าเป็นบริษัทแบบเป็นตอนนั้นรู้สึกยังไงที่จะเป็นบริษัทตรงนี้เลยเป็นดีลเลอร์ชอบเป็นช่างของดีลเลอร์เป็นยังไงเนี่ยผมเป็นต้นเองไปจะโรงพยาบาลเราก็นำเข้าไม่มีทำผู้ใหญ่เองเลยเป็นลูกค้าเป็นทำเองไปกับคนที่มีท่านของการสั่งเราเป็นนำเข้าฟังงานได้ทำยิ่งเลยทำเรื่องต้องมีการนำเข้าเกณฑ์อยู่แล้วเข้าเริ่มคิดว่าจะมีหลายอย่างครับบอกเพราะว่าตั้งเป็นดีหมดแต่ที่มันใส่อะไรเยอะการแพทย์ฟ้าอะไรให้เป็นได้เด่นฉากลองไปไม่เดิมครับเป็นบอกว่ามันมีเขามันทำเป็นมันมีเจ้าหน้าที่อยู่แล้วเป็นบริษัทเขาซื้อระดับเขามาบริษัทในเขามีเป็นประเด็นคือเราซื้อเป็นสื่อถูกไหมเราต้องได้ทำบริจาคเราซื้อเสื้อแต่ผมกันมองคือเขาบริจาคให้เราเป็นคุณจีใช่ถึงบอกว่าเราไม่ได้มีกระบวนการจัดซื้อในอันนี้เลยเพราะเรารอว่าท่านคุณจีจะคุณก็คือเหมือนคุณแล้วเวลามันทำจริงก็เป็นบริจาคท่านจีเนี่ยจะแทงช่องเนี่ยมีความสำคัญกันไหมไม่บริษัทจีนเนี่ยเท่าไหร่ก็คือเป็นแต่มันอยู่เป็นเจ้ามันมีอะไรที่ว่าจีนขอเอาพวกแต่เป็นสิ่งอะไรอย่างเงี้ยแต่ถามว่าเขาจะได้ไปต่อในครอบครัวไหนต้องแบ่งคนว่าเขาจะขอแชร์แต่ผมเห็นไอ้ก็ขอห้องช่วงเวลาที่เป็นไม่เหมือนเราเป็นเงินเข้ามาก่อนไม่ให้เวลาขาดเป็นของเราเหมือนผ่อนจ่ายเวลาเราอะไรที่ไหนอะไรไม่แต่เขาเป็นขอ
ปีทางที่ก็คือแบบออกแบ่งใช้หรือว่าออกแบ่งไปได้ครับ
เอามาปีที่อะไร
หมอผมใช้ก็คือใช้
เดี๋ยวอาจจะไม่เอาแต่ไหน
ก็เป็นจาก
แต่แอร์พอร์ตไม่ได้เป็นให้โดยตรงเป็น
ก็เลยตัดเองก็เลยว่าความสามารถของตัวเองแบบได้อะไรเนี่ยเขาต้องบอกเงินเลยจ้า
วันนี้เขาบอกที่ตามอะไรนะคนนี้คนเดียวชื่อไปกินข้าวครับที่ขอข้อมูล flexibility อะไรต่างๆเราไปเพื่อเอามันเป็น
เหมือนกับว่าเราคนไข้
พอที่จะมีเรื่อง
หมายคนไข้เป็นเบอร์ใดให้เป็นเป็นยังไงอะไรอย่างเงี้ยเพราะเขาเป็นติดคำนวณว่าเขาจะใช้เร็วแบบไหนให้เขาได้ผลแทนการยังไปแสดงออก
เป็นบามาเดี๋ยวชื่อเรื่องเอาก็ดูเหมือนจะให้เป็นเบาสีหน้าก็ดูเป็น
เวลาแบ่งกันในแต่ละส่วนของช่วยกันหาคนอารมณ์ขาดไอ้ดินะก็ที่ตรงนี้ถามการต้องรู้เที่ยวได้ประเด็นเนี่ยไอ้คนละ100 ล้านติดด้วยเพราะไอ้เนี้ยที่ภาพเรื่องนะยังแบบถกเถียงกันแต่เรา150ทำตีนนะ
วันที่เราไปเช่า
เขาทำตีนและถ้าเช่าแล้วไม่ต้องจะไปเอาไม่ต้องเสียลงทุนการให้ทำตีนเอาเข้าได้เราก็เดี๋ยวเราดูตอนช่วงเปลี่ยนการอะไรนะเป็นปีสำเร็จมันไม่เสื่อมหายเพราะว่าเช่าเป็นราคา10 ปี
ไม่มีภาษาอะไรเลยก็มีก็คือแบบจะบอกเลยเขาปล่อยไว้ที่ตรง
See, the microphone is working.
So this one, this stage is going to be the general feedback from those presentations. I took some notes and, I'll kind of put that in a little bit of a report later. The one thing I don't know, will they give you their presentations? Because if they give you the presentations, I like to go through, look at them a little more in detail because, just looking up, it was kind of hard. Yeah. You said, and I go through a little more in detail. The main part is that kind of the design they have, and even the injector, like they said, was from Hitachi, and they have the filament source instead of an ERS. So Hitachi did that just so they don't give them their latest technology. But that synchrotron, if you look at that synchrotron that they have, that's almost an exact same design that Hitachi had in Nagoya and the MD Anderson one, right? So they're the same. So the synchrotron itself is good. And you probably noticed, they have the 8 dipoles and they have a lot of quadrupoles. So they have all those quadrupoles in that design probably because they didn't know, how hard it was going to be to tune the beam. So that's the part where you're kind of retuning and getting your beam shape, right? The dipoles are bending, but as they bend, you know, if the edge focusing isn't very good, you need the quadruples to correct it. So if you saw, they just had a lot, which is also kind of expensive, but they probably did that to make sure they could have a lot of knobs to be able to turn and tune the machine. Probably what they install here would probably have less number of those quadruples, but in general, that design and the way they describe their extraction, everything else, that's basically where Hitachi was in like 2005, 2007. So when they describe their extraction, so that's what has been published. Again, if you go through the publications, you'll see that that's a method for proton synchrotrons to extract, and that was something published, I think, in like 2002 or such. So they're using that method. And NRS or QST now, and Toshiba and Hitachi currently use a similar system. It's still an RF knockout, but it's a little bit different. So they've learned throughout the years of how to improve that system, be able to extract more. One of the things he said was, you know, during their extraction, they have about an 80% loss, right? That's high. So right now, they probably can't really do multi-energy extraction because when they are doing this extraction, they're losing a lot of beam. They're probably learning about that and trying to modify and trying to improve that one. They were saying when their beam changing time, you know, to change energy into single energy extraction is the same as any of the synchrotrons, right? It takes them about 1.5 seconds to dump the beam, refill it up, goes up about 1.5 seconds. So it's about 2.5 to 3 seconds when they say, you know, stop, dump the beam, about 1 second to 1.5 seconds, refill it up, go to an energy about 1 second or 1.5 seconds. So their energy switch time right now is going to be about 3 or 4 seconds. And they said they're doing single energy extraction. They've tried multi-energy extraction, but as you saw, their beam quality goes down really quickly. So when they showed the oscilloscope, so that's because their extraction method, they're really perturbing the beam. They're even getting a lot of loss when they're extracting. So they can't actually, there's something called a recapture efficiency. So you have a beam going at a certain energy, and once you extract, you know, it makes the beam kind of fuzzy. And then you have to kind of retune that beam a little bit and step it down. And when you're doing that, you're going to lose some. Hitachi initially, when they started multi-energy extraction, and multi-energy extraction for proton is hard. It's actually easier for carbon because the beam in there is physically smaller. You know, protons are kind of hard to squish them together. So when Hitachi first started, you know, they only had the single energy extraction. So when you go to the older MD Anderson, which is basically that same synchrotron layout, they had a hard time doing multi-energy extraction. They did eventually get it, but their recapture efficiency was something more like 40 to 50%. So they only have so much protons in the beam, and then they extract. Hitachi's initial extraction was cleaner than this. That seems kind of high. Maybe he missaid the number because that seems high. Maybe it's actually 20% loss each time, and he's saying 80% efficiency, but that's not what he said. He said 8% loss. So I'm a little bit confused. So that's why I want to see what the actual numbers say, and it could just be his English translation. But Hitachi had only about 50% recapture efficiency, 40 to 50%. So every time they stepped down in energy, they would only be able to get like half the beams. Then they could only go down 1 or 2 energies before they didn't have any more beam in. Now, currently, and just talk about Hitachi, since Hitachi has the only other one that has a proton synchrotron. The other ones, the Russian design doesn't actually count because they don't do multi-energy extraction. Right now, Hitachi's about at 90% recapture efficiency. So it's just throughout the years, they've just learned. So again, that's why they're kind of where Hitachi was in maybe, you know, 2005, 2010. They will learn as they're doing their system to be able to extract better, recapture better, and such. It just depends how long that's going to take. And really, is it going to take them really in your system to learn that, you know, or are they going to learn it before you get it installed? And that's just unknown. They should be able to ramp up faster than Hitachi did because Hitachi did it for the first time. You know, no one else had a proton synchrotron and did this. But when they showed that comparison between Hitachi, you know, and even though it said male Hitachi, that was from the contract in 2010, right? So that's not the 2024 or 2025 numbers. That's the 2010 numbers. The spot size is fine. I mean, you're able to squeeze that, and Hitachi's old spot, like in MD Anderson or the other centers, were big because they had both double scatter and they had scanning. So there's just a bunch of stuff in that nozzle. So the spot size is fine. You know, they could probably make it a little bit smaller, but I think that one's okay. The main concern really is, as you saw, they didn't really talk that much about their dose rate. I mean, their scanning magnets seem fine. They seem to scan pretty good. And that's why when we ask these questions of them a little more specific in written, because sometimes when I just know this working with Japanese, when you ask a question in English, it's hard for them to really understand and then answer in English. So when it's written, it takes more time and they can really, you know, give a proper answer.
ใครยอมทำ MOU กับเราสัก
ไม่มีให้ได้
ยากค่ะปิดช่วยปิดใหม่หน่อย
Oh, good now? Okay. Let me see the other notes I put in here. So I'm saying all that because I think where they're at now, depending how fast their learning curve, you know, if you're installing something, you know, start this project 1 year, 1.5 years from now, by the time they install, maybe during that time they've learned more and they'll be able to extract a little bit better, be able to do multi-energy extraction. It took Hitachi basically from 2005 to 2015 to really get good at that. So that was their ramp up. But they were the first ones. Now that it's known that it could be done, and there's some publications out there giving hints of how it's done, at least they know it's possible and they can work towards it. So maybe they'll be able to ramp up faster. But those are things I think you want to be conscious about when, you know, maybe entering the contract or talking about these, that maybe they will spend more time, you know, on those access hours. Maybe they'll need more time, or maybe you want them to use more time to try to figure these things out to make the system better. You know, are they willing to put that time in the one you have to eventually get you multi-energy extraction, where you can extract and have recapture efficiencies of maybe 80% or something like that, and have that in the contract that they work towards. This again, the Synchrotron itself, and they're going to develop their own injector. Like I said, if you put it in, there's always going to be something new, right? So, you know, exactly how that's going to work. Are they going to be able to get it as efficient as the one they have? You know, if they're using the new source, and that's what it's talking about in the cyclotrons. IBA used to use that same type of filament source, and it just, especially in the cyclotron, they just burn out really quick, and you have to go in and replace them a lot more than they thought they would. That's why they're probably moving away from there. And again, designing a LINAC is not easy. So they're designing it essentially from scratch, and hopefully designing a 7 MeV with the RFQ and the drift tube. Because the lower the energy the LINAC is, the harder it is to get the, you know, the admittance and acceptance. So the LINAC only produces so much. It produces a lot of protons, but if you can't match it well, and the lower the energy, the harder it is to match. So I would, you know, make sure that if you're going this way, that they are giving you a 7 MeV injector and not like a 3.5 or 4, assuming that they're able to design a 7 MeV with a new ion source. Yeah, so that was 80% loss. Their method of extraction, like I said, that's the very, it's the RF knockout, but like they said, they use the third order. That's kind of a little bit older mechanism. That's when they are getting a lot of losses when they're doing extraction. What happens is, in theory, that's the one that's supposed to work the best, but in practice, it kind of doesn't. And as Toshiba and Hitachi have kind of learned this, and they moved, you know, perturbed it a little bit and found a little bit better way. They did notice, so they did mention it, but it is the compact gantry. So if you noticed in there, they had the couch, and the couch barely would fit in there. But if you had the patient's head at ISIS center, that couch isn't going to fit in. So with that system, you're not going to be able to do vertex fields. You know, there's ways that are probably around it, kind of get it. If you really need it, you might be able to put in a shorter couch top or just different things, but that's their standard system. So maybe it's something that you want to be able to discuss with them and say, maybe one of your gantries might not be the compact, maybe 2 are compact ones, not so the ones that you are going to do this vertex fills for SRS brains or just typical pediatric brain treatments, you'll be able to do them, or at least work towards how you figure out to do these type of fills. They hadn't done their cone beam yet, so there was no kind of information there. Like he said, there's all kinds of algorithms, everything out there, so there shouldn't be an issue. But if they are doing it in-house, the first time you do this, it is going to not be so good. The reconstruction methods, and you can't just take what you did at a LINAC. I mean, I wouldn't agree with him when he said that it's different from a proton. Proton and LINACs and photons are different. The difference is because of the SAD. The imager and the source are physically further apart in the proton machine. So it is different. It's not necessary that you need to reconstruct or do something special for the proton reconstruction. You want a good reconstruction so you get good image quality. But it is different. So you can't take exactly what you did in one machine, a photon machine, and just transport it and that it would work in the proton machine, because the distances are different. Depending on what filters they're using, will be a little bit different. But they said they're working on it, so hopefully soon. I think they said their gantry is already installed, and they're going to start treating patients in a few months. It sounded like maybe I misunderstood, but at least they'll be able to see how they're doing there, what their image quality is. And then you asked the question about how long they can hold their beam, that 8 seconds. So that, again, that's where Hitachi was in 2010. They'd be able to hold it. Now they could hold it for 400 seconds or whatever. And they said when they're doing their gating, they do one of 2 ways: they either hold it for as long as they can before they go, or their typical way is to dump the beam and refill it up. Again, that's how Hitachi initially did it. So they're on that same learning curve of how to get there. The more they do and the more systems they put in, the more they'll learn how to make their system better. It did sound like they're making a full test bench, and that would be great, because it sounded like they're building essentially a warehouse where they could put the synchrotron in. And they're saying they want to be able to put the synchrotron in and test it, so then before they ship it, it's mostly done. Every time you put it in, you have to retune everything anyway, so I don't think there's really time savings there. But if they do have a test bench, then they could have full access and really start checking these different mechanisms, try to do extraction better, try to solve the MEE. So it does seem like they have a setup to kind of maybe solve these problems quicker than Hitachi was able to. So again, saying that mainly because fundamentally, I think the system is sound. There's nothing about that system that's like, that's, there's some major limitation. It's just they're not on that learning, they're starting the learning curve. They're not there yet. I was a little bit disappointed that it seemed like they're trying to focus on a lot of things. If it was me running, I'm like, we have this proton machine, let's make it as good as we can make it. They're working on this LINAC thing for flash. They're working on proton CT. Again, I think the physics of that's interesting, but the practicality of it is not very good. You're going to use a whole treatment room to do a CT, and when you look at the actual publications of proton CT, you're not able to get the stopping powers any better than you do with a good dual energy CT. There's just the proton scatter, everything else, your reconstruction is not that great. That wouldn't be where I would be spending resources. I'd be spending the resources on getting my extraction and multi-energy extraction better, and doing my cone beam CT and making sure that's really good. Saying they're gonna spend the time with the LINAC, with these other things, and then their collaboration with Toshiba, so they're moving forward that maybe they want to get into being able to do carbon eventually and such. That's kind of a natural progression, so that seemed reasonable. But the more engineering time they're spending on these other problems, they're not spending solving their fundamental problems. And they admitted that their extraction is not very good. They aren't doing MEE. So hopefully they are spending time on that one. Yeah. Yes. Yeah, I mean, it was a little bit lower than I thought it would be, given that they have a 7 MeV injector. But that's coming. I want to see the numbers because maybe they actually have a large number of protons. You know, maybe the current that's coming out of that LINAC is relatively high. Yeah, and that's why I have to go back and look at the numbers to really know. You know, because it's like there's so many 10 to the 8, 10 to 11. This, you know, factor of 10 is very important. So this company didn't want to necessarily comment on those numbers yet till I have a chance to look at them and compare to other systems and see what's happening. It did seem like their storage was relatively low. I would have expected. So since they do have the 8 dipoles, it is a relatively large ring. So Hitachi's current proton design is just the 4 dipoles. So it's really tight. And it's, you know, the smaller you make it, the harder it is to actually fit protons in there physically. You just don't, you know, they're in buckets. So you just have so much physical space also to do this and to be able to accelerate them. So I thought they'd be able to actually have more beam in that synchrotron. And Hitachi's initial design also with that large one is because for double scatter, you need a lot of beam to be able to come out because you're wasting a lot. You're blocking a whole bunch and all these other things. So the Hitachi system that's kind of that design, going off of memory, that's I'll just say right now, it's going off of memory, so it might be wrong. They could hold many more protons initially. So that's why I want to go back and kind of check these numbers and see. And maybe it is coming then from their efficiency from the LINAC going in. So I again, fundamentally, I think the system is sound. They just have a lot of learning to do. And the question is, are they going to do that learning off of your system? You know, if it is a second system and that's the learning curve and maybe, and you know, you guys learn together and it goes forward, or are they going to be able to solve a lot of these problems or at least make good progress before they install your system? Yeah, you know, the fact that they integrate with the third parties for gating and stuff, that's good. You know, that they already have that. It's usually fairly straightforward. You know, they already have some systems in there and did kind of not really address some of the questions of, you know, when you're storing it and you're doing gating, you know, how long can you store? He said they could hold for the 8 seconds. And that is before they do any extraction. So, you know, they're just holding it for 8 seconds. You know, the question that will eventually pose is once you start extracting, how long can you hold it, right? Well, you extracted a little bit while you're in the gate and now you have to pause. And that's why now they're dumping the beam and refilling it back up, which I lived through that. That's how our system was originally before Hitachi was able to do a little bit better multi-energy in their extraction. It is hard. I mean, you just really can't do gated treatments. They just take way too long. Their dose rate is not very high. It's not super low, you know, it's reasonable. But that means if you have a moving target, you're going to have to do repainting. So we didn't talk about that kind of scenario, but he did show like, you know, when there's motion and you saw this interplay effect. So one way to mitigate that, in a phantom, you can always make it look perfect because the phantom moves exactly perfect, but we know patients don't do that. So a mitigation strategy, there is a lot of motion, is you do repainting. And even if they do a breath hold, you know, there's always a little bit, or if you're doing gating, there's still residual motion. So you do repainting. And what this does is now you use lower MUs for your spot, and you just paint it over and over and over again. So that as this thing is moving, you kind of wash it out a little bit. I think they're going to have real trouble doing repainting. Mainly, he did have a dynamic range that was on one of his tables. That's what I want to look at again. But it seems like they couldn't go too far down, like the min MU. We talked about a min MU. It seemed a little bit like their min MU might be relatively high. It's their own ion chambers. And I know when he talked about that they've sent it off to Europe, those are for carbon machines. And for carbon machines, you don't need to be so sensitive because, you know, one, you don't use as many carbon ions and they react a lot, so you get a good signal. So, you know, asking the question again, I'll do it more in a written way of what their minimum number of protons they can do per spot and these kind of things. Because that's really going to drive. They did have something like they said the maximum SOBP they could do, I think, was like 13 centimeters. They had something for some reason a max SOBP. I think the reason they have that in there is as you're making a spread out bright peak, the more proximal you get, the lower amount you need. And so that it goes to that minimum monitor unit. You know, how low can they actually be sensitive and still deliver? So if they can only make one that's 15, that means they can't go any further because that the beam is so low that they can't detect it. The number they had up there is just my first impression, seemed a little bit low, but again, I want to go back and check that. So yeah, everything he was saying was going through. It was really, it looked like the specifications that Hitachi had for their MD Anderson one. If you take the double scatter out and just look at the scanning, you know, their scanning magnet seemed relatively fast. You know, there wasn't an issue there. Or for written document, we'll ask some more detailed questions. There's something called delay dose. So they're still doing spot scanning, beam on, beam off, beam on, beam off. They're not doing continuous. That would be one question. Are they going to do continuous scanning eventually? The reason that one's important is, again, every time you turn the beam on and off in the synchrotron, you're kind of kicking it, and it becomes less and less efficient. And if you're continually extracting the beam, that's kind of a little bit easier on the machines. So then you're able to actually extract more beam and everything else. But the control system to do scanning, continuous scanning properly, is a little more difficult. That's come everybody started with spot scanning. So is that going to be on their roadmap? Are they going to do continuous scanning? You know, so those are some of the questions we'll end up having to ask. Let's see, there was one more thing. Oh yeah, so he did talk about, okay, so it kind of in dejection, and they're going to redo that whole system. As you saw, when they redo that system, they are, anytime you do a LINAC, what comes out of that LINAC is going to be very different than what they currently have. So it is going to be very interesting to see how that beam matching, you know, right now it's not so good, and maybe with their own LINAC, they'll be able to tune it a little bit better and get actually better injection. You know, when they said they're only able to capture so much in the first inject, maybe with their own design, they'll be able to do it a little bit better. But then again, designing a LINAC is hard. It's, you know, it's much harder than designing a synchrotron. So, you know, that's going to be, if anything's going to delay them or something like that, it's going to be that design. And as you saw, Hitachi gave them an old version. That what they showed there was Hitachi's old version from like 2002 or something. But okay, so again, overall, I think that system has potential. If they really do concentrate on their fundamental problems that they have, which are natural, this is the first one they did. So it's not saying that, you know, they should have had all these problems solved. They got to learn to this. But if they really focus their attention on those problems and not these other things, then I think they'll probably be able to solve them and have a good next system. You know, maybe you do have the second one, maybe you do have the third one, maybe they're already getting something to go into some other China site. So maybe yours is the third one. But that's why the one question of where else are you installing this is important. So you kind of know. And you also know that how many are they doing at once? You know, all of a sudden now they have 4 sales or something. You know, then the engineering team is spread thin. The commissioning team is spread thin. You know, so do you have a new person coming to do commission? This is the first time they've done it? Or do you have the person that's done it 3 times and can really do it really well? So that was my initial impression. I do want to get the, you know, their presentation with the documents. I could go through and really look at the numbers they put there, and instead of just going off of memory, actually compare it to information I have and make sure, because maybe their injection is a really good number, and so forth. And of course, the things he said, you know, with obviously English is in his first language, so maybe, you know, he missaid some words, and it's actually better than the thing he actually said. So that was the first impression. That was okay. Go ahead.
So, from your opinion, what I perceive is this machine is maybe as good as Hitachi one in 2010, maybe 10 years ago, it can be matched with that machine. I just wonder that for the Hitachi at MD Anderson and Mayo Clinic in 2010 compared to the latest one, what is the major difference? Is it a control system or a calibration or the design of the magnet system?
Yeah, actually all of those ones. So the first thing Hitachi did from their initial design, which is basically that design, is they went to a compact form. So it just made it smaller. So it only has 4 dipoles. So it's actually, you know, you put something in there, but the current one is actually much smaller than that. Again, that's a footprint, and Hitachi was working to making a small, small footprint, make things tighter. So the first thing when they went to that smaller one, they learned a lot from their first system, and they actually did 2 of those systems. They had one in Japan, and then the first, I'm going to say the first MD Anderson system, because MD Anderson just put in a new Hitachi system. So the first one had that same design. And when they moved to the more compact design with just the 4 dipoles, so they had learned a lot from that system. And one thing that they did learn is they didn't need as many quadruples. So, and even their first design didn't have as many quadruples as that has. And again, the reason they have so many, and for the first one, it's totally fine. It's because they wanted to make sure they could tune the beam as good as possible. The more quadruples you have, the more knobs you have to tune the beam. So Hitachi went, now they did a 4, and it's just 4 dipoles. And they actually only have like 1 quadruple in there because they realized they could get something really good. What Hitachi kind of messed up on is, since they didn't have so many quadruples, their edge focusing wasn't as good. They thought they had it designed well, and I don't know, like when you guys design, maybe use COMSOL or something like that to do the magnet design. In theory, it looked like it was going to do right, but in practice, they had a little bit of instability. So they learned that, and the next one they put in, they actually just shimmed a little bit those dipoles to get it better. So each one that they did, they kind of improved a little bit each time. So the system that they have in, that the Chinese company has in now, there's nothing about that system that they can't figure all these problems out. So if that synchrotron, and let's say they have a good injector that they design, there's nothing about the physical stuff that prevents them from figuring these things out. What will happen is in their control system is what are they actually allowed to do and what they allow themselves to do. So for instance, if in their control system, are they actually able to change how they're doing their extraction, right? Once they put it in and they say, this is how we do our extraction, within their control system, usually it's kind of fixed. You can't go back and then say, unless you have to take the system down, go in and change that panel, that control system, and say, I'm going to extract differently now. And once you extract differently, you have to recommission everything. Now everything's kind of weird. So if they might set up the system that they have a service or a research mode where they could go in and change that module and do research or development, and then for clinic, change it back to the old way. If they have that within their control system, then okay, during the nighttime, they could continue to work on this problem and try to figure out for the system we have here. If they don't have that module, then it becomes potentially dangerous because now they're playing with it in clinical mode. They could still play with it some, but now you have to make sure that they really went back to the real clinical mode, that everything was working fine when you go to treat the patient. So again, that's the control system design. You know, if they design it that they allow themselves to go in and do these different things, then they're able to improve the system at night and then turn it back to the normal system. And every night go in and do certain things, make it better until they say, okay, now we have this extraction better. And now instead of 80% loss, they have 20% loss. And they figured it out. Okay, then that's an impact to the clinic. So, okay, now we'll do effort and go in and commission that one for clinical use. So again, it really just depends how they design that control system. Hitachi does have it within their control system design not just a service mode, but that develop mode that you can go in. They can go in and do different things, do different extraction, do different stuff, and always change it back to the clinical mode. I would assume they would do that. I mean, obviously they're accelerator engineers and they know clinic versus development, but those are kind of the questions that we kind of specify out. Okay? How are you going to do when you're going to work on improving our extraction or the multi-energy extraction, anything like that? How are you doing that? Are they going to do it at night? What mode are they in? These kind of things, so that clinically, then you know, okay, they're going to go back and forth, and you just have to be conscious about that. Same thing when a service engineer comes on a Linac and they fiddle with certain stuff. They're fiddling it within service mode, right? They're running the thing, they're running the electron beam without the target in there and different things they're trying to figure out. But it always has to go back to clinic mode when it actually comes time to use, and then you have to check it. So those are kind of things of, are they doing that now? Like with the system that they have in right now, are they looking at that? Or are they just trying to tweak little things here and there?
If they finish like to do R&D to improve the control system, and if there is any like if it's possible for Hitachi to change the control system at MD Anderson to improve the efficacy of the machine?
Slightly. So there's usually and this actually comes back to regulation, which is safety, and he kind of mentioned that, right? So you have to clear the device, and it has a control system, and main part of that control system, make sure everything's safe, right? You count protons right, you get the right spot position, all these different things. You don't want to really mess with that part. But once you start saying now we're going to extract faster, we're going to extract more, you have to make sure that the monitor chamber can actually, now you have a higher dose rate, higher number of protons coming through. So that changes. There's an efficiency in the monitor chamber. And let's just say you double it, right? So now you got to make sure that it's still counting the right number of protons. So and that's in the control. That's like the core control system. So in that aspect, they usually can kind of change some parts, but most of them are FPGAs. So they're in there and you program it to do one thing and do one thing right and do one thing fast, right, and nothing else, right? And it does that. And that's for safety, right? Because you don't want something to happen and all of a sudden the patient gets a lot of dose. So in the regulation part, if they go through and now they're going to do a different extraction method, either on the clinical side or on the regulatory side, it should be, okay, now we got to go and do all these tests again to make sure that you are able to safely stop the beam. Now you're extracting the beam twice as fast. Okay, you're extracting the beam twice as fast now. Does that mean you can stop it twice as fast? If you're really close, it took you, 10 milliseconds to stop the beam. Maybe you're at that threshold that you're giving more than the 0.25 gray to the patient. So now you're extracting twice as fast. Are you, if you're still only able to stop at the same one, well, maybe you are no longer meeting the international guidelines of safety. So it's those kind of questions, depending what they're changing. If they're improving the extraction method, like the multi-energy extraction, okay, so you're still extracting at the same rate, but now you're able to go more energies, kind of change them at 200 milliseconds instead of 2 seconds. That's fine. That has no change in the monitor chamber, the spot position monitor, or dosimetrically, there's no real change there. It's just now you're changing energies faster. So that wouldn't be necessarily wouldn't be a regulatory issue. But yeah, if they truly improve their extraction, or they truly improve how much they're able to inject or store, then, if you double that number, then when you're doing your extraction, you can extract more every single time. So what downstream implications does that have? And that's usually where, at least in the US, the regulatory body would want to say, prove to me that you have the right safety things in place now that you are extracting twice as fast.
So it seems that it's quite difficult if we bought a machine, and if in the future, after they have a learning curve, we cannot upgrade to that.
It's generally hard. Some things, like the multi-energy extraction, that's something that they would be able to then implement. The control system does change because now, you know, okay. So when you're tuning the synchrotron, you're tuning every single energy. So they said they had 94 or 97, some number, right? They had like 94 energies. So you're tuning that synchrotron. And let's say there was an energy at 100 MeV and there's a energy at 102. When you're doing single energy extraction, it's tuned a certain way. When you're going to do a multi-energy extraction, when you're going from 102 to 100, that 100 is not exactly the same as a single energy extraction. So they have to go, one thing is they have to make sure in their memory, in their controls, the control system has so much memory. And usually it's set up and say, here's how I am at this energy, here's I'm this energy, this energy. And if they already thought about it and say, we know we're going to do multi-energy extraction, so we're going to make sure we have enough memory to hold it. We can't do it now, but we know we're going to do it in the future, then okay. If they didn't do that, or they did it, you know, just a small amount, then they just don't have in the control system physical memory, and you're not going to go and switch out the chips in this control system. Then it's like, okay, what did I just do? Just messed everything up. So if they thought about it before, like, okay, we're going to do multi-energy extraction eventually. We can't do it right now, but eventually. And then you ask, you know, how deep are you going to go? Are you going to go 5 energy? You know, all these different things to make sure the control system can handle it. Then you're fine. Then you can do it. But if they didn't do that, then you cannot go back and change it. You know, because then it's a whole different beam tune. The multi-energy extraction is a different commissioning than single energy extraction. But that part doesn't have to do with like the regulatory. I would say the regulatory would come into play if they really did do something like improve their extraction by 100%, which it looks like they have a lot of room to be able to improve their extraction. And then you have to worry about the dose monitors and everything else if they're going to be able to perform that way.
Okay. So thank you very much. Actually, I have one more question. This is not related to my previous question, but I just interested in multi-energy extraction. I think this is the first time that I heard about this one, because the machine in the market usually extract the one energy at a time, right? Is there any machine that available now have the multi-energy extraction?
So there's 2 types of machines, synchrotron and cyclotrons. Cyclotrons are only one energy, 2, what the maximum energy, then they use the degrader. So they are technically multi-energy, right? Because the degrader just moves and it's just pulling it out. So with those ones, they don't have that kind of an issue.
Okay.
They take a while to change energies because when they do this, they have to change all the energies in the beamline and the gantry and stuff like that. Right now, every carbon machine in the last even 7 years does multi-energy extraction. It's easier to do it in carbon, again, because when you kick the carbon out, they stay, you know, they're just heavier, so they kind of stay together better. Basically, when you kick the protons, they kind of go everywhere, right? They want to just separate themselves. You know, there's a phase charge effect. They want to go away from each other. Carbons aren't that bad at doing that. So it's easy to do multi-energy extraction in carbon machines. So all carbon machines do multi-energy extraction. They've always done it. The only company that does a proton synchrotron is Hitachi, right? Besides this company. And they've been doing it for a while. Hitachi started doing multi-energy extraction basically in 2015. So when we opened our doors to treat patients at Mayo Clinic in Arizona and Rochester, we started with single energy extraction. They knew they could do multi-energy, but we started with single energy, and then because it takes longer, and they weren't highly confident that they would get it to work as good as they wanted to. So that was the development. So, you know, Hitachi was working on it at night, you know, after we'd be treating patients to kind of do this and solve it. And they had a Japanese site at Hokkaido that they were working on. So they figured it out. And their first instance, they had 50% recapture efficiency. So that means you're at 1 energy and you extract it, and then you step down, they lose half the beam. You know, just stepping down, they lost half the beam. And you already extracted some. So really, you could only go 1 energy, maybe a second energy before it wasn't useful. So it was useful because you got 2, maybe 3 energies out. Technically, there was memory to go 4 or 5 deep, but that's all practically they were able to do. Now they figured out a little bit more, and their recapture efficiency is more like 95%. So they're just more efficient at it. They've learned a little bit more and such. And those are things that they were able to do in development. The other thing they were able to do, like in development, is they started off with, for protons, they started off with spot scanning. They're still doing protons, still doing spot scanning. They do have a continuous scanning method, but they were able to figure out ways that they could make it a little bit faster. You know, be able to extract a little bit more, move it a little bit faster. You know, you have all the safety things that you got to check, make sure the magnets move to where they were going to do all these other things. So they were able to work on that and say we're able to improve it. So that was for the system that was installed, they were able to upgrade to multi-energy extraction, and they were able to upgrade to a faster spot scanning method. But these were things that they were already thinking about and knew that they wanted to do, and it was kind of built in. They just weren't ready when we were opening the doors, but eventually they got there. So it's be the same thing with this one. You know, like I think eventually they will learn how to extract better. You know, first before multi-energy extraction, they got to learn how to just extract better single energy, get more dose out. They got to be able to hold the beam a little bit longer. You know, 8 seconds is not very long if you're trying to do gating and do this thing. But that's where Hitachi started in 2010. They were at 8 to 10 seconds. Now they can hold it a lot longer. So again, and holding the beam, that's not a really control. That really is just instability in the beam. So all of a sudden they figure some of those out, some of those tweaks. There's no major change in the control system. The only change would be that they're allowed in the control system. It probably already has a mechanism to say after 10 seconds, I need to dump. As long as this is not hard coded in, you know, as long as that's something that they could change and say, okay, no, now we're going to change it to 50 seconds or whatever it is, or make it longer. But those that have brain control systems, sometimes some things are hard coded in. You can't change it. So if it's something they're working on, hopefully they've done that. But these would be the questions we want to kind of ask a little more specifically. Like, what is the roadmap for this? Will the system that's being installed, is it capable of doing that without having to do a major upgrade and these kind of things?
Okay, thank you.
When we shift from single energy extraction to multiple energy extraction, did you need to change the hardware or
No.
we use the same hardware?
Same. Yeah, all the hardware was the same. Huh? Yeah, so that was all a Hitachi portion. And like the treatment planning system, so some of the modern treatment planning system has a time component. Like if you could, yeah, you could do an optimization so that you could try to minimize, you know, you could give up some plant quality, but you could minimize how long it takes to deliver. Like sometimes for the lung, you're not that concerned about the conformality, but you want to deliver really fast because of breath holes and different things like that. So then you'd want to know within your treatment planning system that you have multi-energy extraction and it takes so long to do this. But the treatment planning systems that we were using didn't have that time component. So there was nothing on our end that needed to change. The only thing that changed was the delivery was now faster. We didn't have to, you know, dump the beam and refill it up. So like they're saying to change energy is about 2 seconds. Second and a half to dump, second and a half to go up. With multi-energy extraction, it's about 200 milliseconds. So once you're done, you step it down, check, and then you can extract. So that's a huge difference.
How about the beam optic? Multiple
Yeah.
extraction. You also need to change the beam optic of the transport line for measuring again.
Yeah. So that's come as in your control system. You need that memory saved, right? Yeah. Yeah, because single energy extraction, like I said, like the 105 MeV and the 100 for single energy is different than the multi-energy going from 105 to 100. It's a whole different beam tune. So that's why, and it's a lot of memory, right?
Yeah.
We talk about things, but every quadrupole, every dipole, everything has to have different settings. So that needs to be stored in there. So as long as they're able to store that information, then you could do this. And you have to check the beam commission. We check and make sure it's still the same range, has the same label, nothing's really changed. It still measures to within the 1/4 millimeter with your IDDs and such. And we had to commission it, right? There's a new tune, so we had to go and do the measurements, do the spot position measurements and stuff to make sure everything was still fine. But there wasn't and that's part of it. You'll say you want to make sure multi-energy extraction matches your single energy. You don't want all of a sudden now that or you have different ranges and the spot's bigger or smaller or something like that. It should be the same.
Yeah.
Yeah. Yeah. Yeah. And everything's a big look. See, every dipole, every quadrupole, everything has. Yeah. Yeah. Yep. Yeah. Up to the nozzle. Yeah. Say that again. Stepping up. I've actually asked that question. Hitachi just felt for them it was easier to step down than step up. So most systems deliver from higher energy to lower energy. One reason for that is typically, not all the time, but typically your higher energies are using more protons. So if you look at a basic SOBP, those high energy use more. So you want your synchrotron to be full because you can use that. And then if you start with the little one, you did a little bit. And now when you recapture, you're going to lose some more and stuff like that. So it's more on average. But if you did, you can go up, but that is a different tune. There's hysteresis, right? So if you're stepping down, there's a certain magnet hysteresis, and they didn't talk about, but what they probably do when they dump the beam, they go up. They probably go up to their 250 tune, and then go down, so that you always are at the same pattern again. So if you tune it to go down, then it's a different beam tune to then go up, right? It's a different pattern.
Sorry. In my understanding, the multi-energy extraction, its benefit is the efficiency of the extraction and the treatment time that may be a little bit shorter.
Yeah, basically treatment time is shorter.
But we have to compensate with the conformality.
No,
in the
with multi-energy extraction, you get the same conformality. Yeah, it's the exact same, except instead of every energy taking 2 seconds, it takes 0.2 seconds.
Okay.
So, and when you have a lot of energies, as long as you have good recapture efficiency, then you could do a treatment a lot quicker.
Okay.
So that's the main benefit. It's just the patient treatment is just faster. So motion, everything else is just that much better.
Okay. Okay.
How much time that you can reduce for
Yeah, so it was usually about a 30% time savings, but the main part is beam sharing. So if you have 3 rooms, that time is then the time you're able to that much faster switch to the next room and treat, switch to the next room and treat. So it kind of, because you have the one accelerator, right? So typically there's 2 ways you do it. You have 3 rooms. You could do, kind of talked about that, I think yesterday or maybe on Wednesday. You could do the whole treatment, let's say it's a 3-field plan. You could do 1, 2, 3 fields. You could treat the whole thing, the patient did the whole treatment, and then go to the next room, and then go to the next room. And that's not very efficient. The better way to do it is to do 1 field in 1 room, the next field in the other room, the next field in the other room, and then you come back, whoever's ready. Okay, you're gonna rotate the gantry. Some you might want to re-image and some you might not. So then there's a beam queue. Once the therapists are ready, they say, I'm ready for my beam on. And whoever's ready next, the beam goes there and you go. And every patient is different. Maybe they cough, so now you need to re-image them just to make sure it's fine. So you don't want the beam to be there waiting for you. If you have to re-image them, you could treat somewhere else. But that goes to that room switch time. So he didn't actually answer your question how fast they can switch rooms. He probably misunderstood the question. But the question would be, do you switch rooms field by field? Do you do it patient by patient? And then how fast can you do it? And those are better in written form, just so they could give you the full detail. Because and that goes back to the control system. So when you upload a field, so kind of you haven't worked on a regular LINAC, but you get all the plan information. So you have 3 treatment rooms, and every treatment room has a different patient in there. So you get the plan information, and you can only treat one field at a time. So you got to upload that data. And that data then we talked about has to be translated into the thing, get all ready, do the checks, and then you can treat. So the question is, if you have 3 patients and you're ready for field number 1 in each patient, and they say they're ready, is the control system actually have all that information for all 3? And now room 1 says they're ready, and boom, you do room 1 and room 2 is ready. It's already has the information and treats. Or is there a control system such that they can only hold one piece of information? I can only hold one field. So this room is ready. Okay, I'm going to treat. Which room's ready next? Upload the field, do all my checks, go. So that's the control system. And if you're running an experiment, right, you have different beam lines that you're going to run the experiment to. You know, are you set up that you do, you know, the experiment for one room, whatever is going to happen, and then set all your beam parameters so you can do the next room? Or do you have all that information so you can do whatever room you want whenever you want to do it? So it just depends how that control system is set up.
But how about total time? Could it be different between if you do 1 room at a time and do 3 rooms or 6
Oh, yeah.
So,
No, it's very different. So let's say each room has, okay, there's a patient in each room. And let's just say each patient has 3 fields. Okay. So room 1, 2, and 3, we treat field 1. Now, after you're done treating that field, you have to move the gantry, right? So now you're moving the gantry. You got to set up, make sure everything is good, and then beam on again, right? And there's time that takes, and maybe you might want to image in between each one. This is a stereotactic. You want to be really precise. So now that you move the gantry and everything, and maybe you've moved the couch too, you re-image to make sure. Well, all that time, the other 2 patients are just waiting, right? So that's why it's better to field. You did this field, okay, whoever's next, I'm ready to treat it. Now you rotate the gantry, do whatever you're gonna do, and if you're ready, and maybe that same room is ready for the second field really quickly, and the other 2 aren't, right? Patients walking out of the room or walking in the room or something. So it's just whoever had that beam queued to say, I'm ready, you know, give me the beam as soon as you can. The logic should be, okay, you're ready, I have your information, treat. And if you only do 1 patient at a time, it's going to be really inefficient. Well, as long as they do it right. Hopefully not. Yeah, that just. Yeah. So, for example, when you upload that information, when the therapists are in room 2. Even though you could treat this patient in room 1, 2, or 3, it doesn't really matter. But once you're in room 2 and you upload that information, it has a unique thing to say, I'm in room 2. And even when you do a real-time patient 2, what comes back is, hey, I set all my parameters up for room 2. And I'm in room 2. You know, you don't want to set the parameters up for room 1 if you're in room 2. So, and that's why it depends how they do their system. They can only do a patient at a time, because they don't have this logic built in. Then, okay, there's this patient, I'm going to deliver this, I'm done, then I do this next patient. They probably don't do that because they've seen, I mean, they have the, in Shanghai, there's the carbon center, and that's an old Siemens machine. And I'm pretty sure that system has I think they have 3 rooms, 2 fixed beam rooms, I don't remember. But it did the same thing field by field. So I have high confidence that they do things field by field. But, you know, those are some of the questions we just asked in there.
Okay. The average. How could we know is the first child?
Oh, so, yeah. So the Hitachi system and the IBA system has this too for their multi-room stuff, is you have whoever comes first gets it. But you are able to, and this is up to the therapist, particularly Hitachi, you are able to say you're high priority. So if you have a pediatric patient under anesthesia, you're going to say you're high priority. And if you're ready, and the other room was actually ready and should have got it, but you're high priority, it would default the logic to give it to that room first. And the third, you know, they should get along. If they always say I'm high priority, I'm just going to make them mad and say, hey, you know, stop doing that. So, but you know, if you have, and sometimes you do that for some other breath holds, right? You have the patient on there, you're like, I need to get this one done because they're about to just get up and leave. I need to finish it. So yeah, the Hitachi and IBA system, I'm not sure about the variant system for the multi-room, does have a thing that say high priority. The system I think we have to is just normal or high. You know, some people have talked about having low, medium, high. And I don't know. You know, there's usually just two. And but that is a good question. That is something that they should have in there, because if it is a pediatric patient under anesthesia, you'll probably, and it doesn't mean you're high priority that you're always going to get the beam, right? Because you did filled one, the other one's ready. Well, it could go as long as they have a fast room time. You know, if their room switch time's like 8 seconds, yeah, okay. By the time this go, I could go and treat the other one and then come back. It's just more like, okay, 2 rooms are actually ready. This one's high priority. I'm going to go to that. If it doesn't, then it uses the logic, whoever said I was ready first to go to.
But that's a big thing, right? Because I'm going to share to be anyway.
Yeah.
My understanding, there is no such priority because.
Yeah. So let's say you're treating in room 3, okay, and now room 1 and 2 they're both ready. Room 1 has a pediatric patient that is under anesthesia. They're going to say I'm high priority, and even though room 2 was ready first, they're going to say I'm high priority because I don't want my patient under anesthesia for a long time. So then it's done in room 3. Normally, it would say, oh, room 2 was ready first. I'd go to room 2. But this one is high priority. I'm going to go to room 1.
So that means every field will go to room 1 first. Every field.
No, because it takes time. So after you were high priority, right? Okay, it's going to take some seconds, 10 seconds, before the gantry has moved and before it's got all the data set for room 2, for field 2. But room 2 was ready. So it finished room 1. Again, as long as the room switch time is fast, then it will say room 2 is ready, room 1's not, I'm going to go to room 2.
And then when it's ready to come back to room
1. And if they're high priority, yeah, then they're ready. They'll go back to room 1 and wait for room 3 till later.
Just wait forever.
Yeah. And that's why you only use the high priority when it's really important. Yeah. Yeah. So usually we only do it with the pediatric patients. Same thing, in your beam lines, right? Everybody wants the beam right now, and it's like, if everybody says, "Oh, I'm more important, I need the beam," they'll be fighting. And therapists are the same way. They're like, no, we got to share the beam. So it's a useful thing, because there are times when you really do need that beam there as soon as you can possibly get it. So it's something that should be included, that is not used that often, but it does actually become a very important thing. And sometimes you need it, like if you have a certain patient that they're there and they're, some patients are in pain. Well, they're down, they're laying down. They really can't stay there that long. And then the team knows that. And they're like, I need the beam as soon as I can get it. So that you do use that, use it rarely, but when you do use it, it's very important.
When you say beam on, that means when you turn it on, that means you start pulsing the beam starting from the up source to the.
Depending on their setup, yeah, but basically that means, so there's usually a couple stages. You do the beam. It's usually called beam queue. That means you're in line. Everything's ready. I'm queued up. I'm all ready to go. I'm in line waiting. And then when it's your turn, it's going to say, boom, you're ready. And then the therapist says beam on. And beam on means, okay, you're ready. And this is the first field you're treating in here. So that's okay, now I got to, put a certain energy into this, get into Sigtron, go to a certain energy, start extracting. Yeah, because you can't be storing it, because it doesn't know beforehand what energy you're going to do, right? So it starts from the beginning. And also, anytime you dump the beam, like I said, you generally go up to your highest energy, then go back down, so you have the same hysteresis section.
And that could be possible if two by different energies. So first it goes up.
Yeah. So generally, the way I've seen it done is field by field. I never seen it done where it'll do part of one field and then move to part of it. Yeah. Yeah, the energies would be different. It does the whole field, and maybe this field needs 150 down to 100, but the next one's going to need 220 down to, I don't know, all the way down to 70, or it's a big field, whatever it is. So each one is different. They're always going to be totally different. So each field is going to have their unique energy list, spot list, and protons per spot. So everything, and every patient's unique. I've actually never seen a plan where you actually had the exact same energy pattern or spot pattern. So it's always different. But that is why that's why I have the two things: the field time and the room switch time. And generally the field time. So if you're in just one room, you have one room. Right? You don't have two other rooms, right? You just have the one room. There's still an amount of time it takes. The plan is there in their system. There's still an amount of time it takes for them to upload that, set the control system. They have to do checks, right? Check everything's good, set up, get the whole system ready to do everything, right? Because it's not going to say, oh, here's spot one. No, pull up, here's spot two. It has to load all that information, the whole spot pattern, the whole energy pattern, the MUs per spot. It loads that whole thing up. So a poorly designed system is going to take a long time to kind of get this information, parse it, because some is for the scanning magnet, some is for the synchrotron, some is for this, that, there's all kinds of different, the gantry position, all these things. So if they design it good, you could really load that information up, get it all set, do all your checks really fast, few seconds. If you do it poorly, then you're like, oh, this takes forever. And so that's the field switch time. So I treated field one. Now I'm going to load up field two. How long does it take till I'm actually ready to do the beam on field two if I just start? And that's different than now field two is maybe already set up in room two, and I just finished one. How long does it take for the system to say, now I'm going to a new room? I have this information for the field. Is it already uploaded and ready, or do they have to do it one at a time? Now I'm in room two. Now upload all the information, get it all ready, and treat. So that, again, depending how they design their system, I know IBA and Hitachi, they're able to load most of the field because the biggest part is the spot pattern. You have 20,000 spots, and they all have a different monitor unit, right? So that's the scanning magnet and the gantry position and stuff. The other one that's the system is what your energy layers are. So you usually don't load up your energy layers, right? It's set, but you're treating in this one. So it's not ready to, but once it's done, it's like, okay, here's my next energy layer set. The synchrotron just cares about what energy layers it needs, right? The other thing is, okay, now the scanning magnet cares about the position, and the monitor cares about how many protons are going through. So there's things that are machine-based, and that's usually just the energy layers. And then there's things that are field or room specific. That's like the spot, and that's most of the memory is your spot pattern and everything else. So again, depending how they design their control system, they could have it, 95% ready. It goes to that field, they do the last check, and then they're ready to treat. Or they don't, and they have to load everything up, and it takes time. So, I mean, technically it's possible, right? So that's why they should have internal checks, right? So here's the instructions I got. I set everything up. I'm going to recheck and make sure everything is set up right. The part that we usually do, like for patient-specific QA, is every patient is different. Again, no patient is going to have the exact same energy list or the exact same spots. So that's the first time that machine has seen that specific instruction. So do a patient-specific QA to make sure that there wasn't some, just say, misunderstanding, right? You asked for a spot position of 10.22 centimeters. It's first time that's been asked. It got it somehow, for whatever reason, it truncated it and it went to 11. I don't know, make something up, right? Okay, so that it did it wrong, and you want to catch that. The other thing is there's the monitor chambers. Okay. When I showed how many protons it takes for every energy to get an MU, the first thing is if it was the wrong energy, that means the whole system had to be set up wrong. So everything's a lookup table. Okay. There's lookup tables for it. So the magnets in the gantry, each one has their own lookup table. And the synchrotron, each magnet has their own lookup table. So when I say I'm going to do a 105, energy 105 MeV, you're telling each of these systems, get your lookup table for 105 and get ready to set yourself the current that's going to go through. So what would have to happen is each of those things have to be set up wrong. Because if you ask for 105 and actually came out with 200, it can't really make it through, right? The magnet will be like, oh, you're going to hit and you're not going to see any spots coming through. So that's one where it's really hard. Maybe if you ask for 105 and you actually set it up and the synchrotron gave you 102, maybe 102, some parts of 102 would make it through. The second check is then the scanning magnets are really sensitive. So if it's 102 versus 105, it's going to go to the wrong position. And that's where you have a spot position monitor. That thing says I should be at 10 centimeters in X. And I'm not. I'm actually at 9.5. It should throw an abort to say I'm at the wrong place. Something's wrong. I don't know what it is. I'm at the wrong place. The other part is you saw for every energy, the amount of protons it takes to make an MU. And you usually do fairly small. You're not doing one spot doesn't have a huge dose. It's very different. So it's going to kick off an error because it's going to be expecting so much. And there's same thing with a photon, there's a timer. Or usually, I'm going to assume they have a timer that says it should only take, a quarter of a second to do this. And all of a sudden it's taking longer, the timer will kick in and say, stop, something went wrong. So if you had the wrong energy and now more protons are going through because of that stopping power, that curve, the timer would kick in and say, wait, this is taking way longer than it should. So that's the second check to make sure you'll deliver a little more dose, but not a lot. That's the thing, that each of these spots are relatively small amount of doses. So luckily, it really is kind of hard to get the wrong energy in, massively wrong. You might get it slightly off. Now you're 1 millimeter, 2 millimeters off. But even there, it's really hard for the spot position monitor then not to be off and everything else. So saying all that is like, if you did somehow load up the wrong thing, it got mixed up. The whole system would have to get totally mixed up. The spot position monitor, it had to get the wrong instructions, and that could happen on the LINAC, right? You have many patients and you load the wrong. That happened before. So.
Expect that in the proton therapy history?
Not that I know of. I don't know of one where that wasn't a human error, like the human says, this is patient A and I loaded up patient B, right? Besides the human error, I don't know of one where they actually had the wrong thing set up. And like IBA does some extra checks. They do a test beam, which I think it's interesting. It's a nice solution. It's kind of weird. But they do, right before they do the beam on for the particular energy, they send a little bit of dose right down the center so they could get a feedback to check if that was the right energy. So if you have an IBA machine, your patient is always getting a little bit extra dose right down the central axis, because they do a quick test just to make sure that that's the right energy going through. It's very, very small amount. It washes out the whole thing, but they do that. Hitachi doesn't do that. I don't think Varian does that. I'm not too sure. But go ahead.
I did design a control system with a feedback from monitor. It seems like a control system together with instrument.
Yeah. So the IBA has two kinds of feedback. One, they have the one where they're checking the energy, but two, they have for their spot position. So the spot position is always slightly off, right? You have a tolerance of it being within, half a millimeter or something like that. It's always slightly off and it drifts a little bit. IBA doesn't have a very good tune in their system, but that's separate. So they have a feedback loop where they're actually looking at that and seeing, yeah, I'm slightly off this way. They're going to change the magnet setting to kind of bring it back thinner. So they're constantly looking at that to feed it. Hitachi doesn't do that. They don't have that kind of feedback loop. But their system's fairly precise. So they don't really need that system. And even the IBA system, very rarely does that feedback actually change by much. But because they are, with every rotation gantry and, when you're rotating this, when we talk about 0.5 millimeter, even the spot position monitor itself kind of shifts slightly. So they have a lookup table to adjust all these things, and that's what they're checking when they're doing this, going to the feedback to make sure it's right, and they'll slightly adjust.
To avoid this accident, could you show me how to improve the interrupt in the control room?
Yeah, so their control system has a lot of interlocks. And the thing to go and see on the clinical side is to make sure that their control system isn't warning you about a bunch of things. So I'm going to guess like at the synchrotron source, when you're the control panel, there's a lot of things like beep, 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 which really means like, hey, it's actually okay. Things are going, but it's slightly off, but you can still do your experiment, just weren't. That's very distracting when you're treating a patient. If you have these things constantly going beep, beep, this is wrong, ignore. That's not a good thing. That's not a good thing to have in a therapy part, right? Because the therapists need to concentrate on that. There is the people in the control room, the accelerator control room, like the Hitachi engineers or their engineers, that are looking at this thing, and they should be seeing these warnings that, hey, the beam, instead of it being 105, it looks like it's 105.2 or something. It's not exactly going the orbit we think. It's slightly off. There's the beam position monitors. They should be seeing this, so then they know, hey, at night I got to do a little bit more beam tune and this kind of stuff. So they should be seeing all these beep things. But the therapist in the control room, they should always see something if something's wrong. Or else they get to that case of ignore, then something is very wrong and they hit ignore and they get blind. Yeah. Yeah. And then the first systems are really designed from, these physics experiments. So they were used to, you want to be able to see all these things, right? But as a therapist, that is meaningless to you. It's like, okay, is the beam going within specifications where it's supposed to? And is my patient, they're looking at that, they didn't cough, they didn't move, everything's going okay. You want their focus to be on the patient care and not on these other things. Yeah. So most systems have that you go into a service mode when you're doing these different checks or doing these beam tunes, because you're doing a beam tune, you don't want it to throw in a bork. You're tuning the beam. Yeah, it's not right. I'm tuning the beam. I'm changing things, and that's a service mode. But in your clinical mode, you need all the parameters locked down, and that's something that physics checks too. So sometimes there's even a physics mode. So either on an annual or maybe a monthly basis, we want to check. There's 2 dose monitors, and we want to check that, okay, if dose monitor 1 is reading off and dose monitor 2 is okay, but dose monitor 1 is reading off, does it actually throw in a bork? Does it stop the beam because something's wrong? So you need a physics mode to be able to go in and say, beam ME1, monitor 1, I'm going to ignore you right now. And I want to make sure monitor 2 can actually do the abort, right? And you do that on the Linux, right? You check to make sure that different things happen. So you have to make sure that happens. And if they don't have that kind of override in a mode, you can't do it. You can't check it. And this is part of the responsibilities to make sure these major interlocks actually are going to work, that they will actually stop the beam and you check it so often. Because they come in and service, like they said, every night they're doing something, every weekend they're doing something. It's their responsibility to make sure everything's back, but sometimes things happen. And on the clinical side, you want to make sure that it's all right. And that's why that Day3 QA is important. I don't know why they need 2 hours for Day3 QA. personal machine, they're checking things and they're doing a lot. But really it is, you have that one phantom and you put a field in there, and you can test multiple energies, multiple spot positions and just check, okay, everything is working okay. You gave the amount of dose I was expecting, you do a low dose and a high dose one, and the dose that you were expecting to receive, you measure it, do you get what you thought you were gonna get? So at the beginning, their personal machine, they're probably checking a lot of stuff, which is totally fine. And maybe the first 6 months, you'll get checked a lot of things, but after a while, you'll get to the point of, okay, we need to check less and treat more patients.
Okay. I think in the schedule, you said we have the next step for the last section. What is it?
Oh, yeah. So, yeah, it's just, yeah. Yeah. So that, just so what, as far as you guys are concerned, what is the next step? So normally at this point, I would think the next step is actually to send out some sort of RFP, right? To this company, ask the questions, detailed questions. Again, depending on the relationship, you just ask the questions of all these things that you want to know. I think it'd be useful to send an RFP to like an IBA and Hitachi. And it probably won't be useful to send to anybody else. But those I think are the two. Maybe Sumitomo. I don't know if they're interested or not. They are in Korea and such. So normally that's what I would think would be at this stage. I would think that would be the next step. But again, that was that kind of the opening. It was more of a question for you guys. What is the next step? Where are you at? I mean, do you have permission to ask other companies to come in and give this? I know sometimes there's sensitivity, even though these are confidential, just to know, people will find out that, Hitachi is going to come and give you a presentation. Yeah, it'll be known. What's the sensitivity? I don't know. Will the negotiation with their dean and this company, would that put it in jeopardy or not? So those are the things that you guys have to talk to them and figure out. But normally it would be okay. We've had these presentations. I kind of have a good idea of where you're at. You're at the stage. There's more information. You're at the stage that you need detailed information, not a 30-minute presentation where they throw these things up. You need something written down with details that you could ask questions about. So I would think the next one, kind of when I wrote out the RFP, is the next thing is to contact these different vendors, IBA, Hitachi, Sumitomo, and then say, one, we're going to have RFP. You just contact the person and say, who's the right contact? We are really interested in a proton system. We're moving things forward. Who do I send this to and get the contacts? So that was
for RFP. You will review for us again or add some question, or this is enough for your part already?
No. So I think based on this one, what I would recommend is you kind of look through it and add some things. Like I said, I would do the RFP to this China company differently. Because so it looks like it's probably not going to be a standard transactional, right? The other ones, that's more transactional, but I think you would ask them if this is of interest, like Sumitomo, are you willing to have some of your magnets manufactured here? If this is something that's important to you, and maybe the answer is yes, maybe it's not. I don't know. I don't know, but these could be things that are, that was kind of on that yesterday. We didn't quite get to it, but the requirements and restrictions. Maybe one of the, I don't know, maybe a requirement is in general that, your academic institution or scientific institutions should be tightly integrated. So maybe they are manufacturing part or whatever it is. So those are the kind of things I think you can kind of put in there. And then I could go through and kind of modify and reword some of the things. And other things that you're interested in. For example, again, I don't know if the pediatric population is going to be a big thing for you here. For the proton therapy having, my assumptions is that it will be. But again, if it is, then you have to add some questions about anesthesia, specific on them. how do you do a vertex field? Can they have at least one that's going to be a larger gantry so you could do these kind of things? So it's kind of that part. And I think the next steps is really, well, two is if that is what your timeline is, in that RFP, I just made up a timeline. So you have to look and see if that's reasonable for your team. And the second one is, okay, at which point are we would get together again? And I think it'd be the in-person meeting once they've responded in writing, that way we can look through and go through and see what they mean, see what they're saying and so forth. And maybe only one company is willing to, respond to it. But sometimes they're not in a position or whatever, for whatever reason. But I do think it just goes to have something of, again, like I said, the specifications they showed were Hitachi specifications in 2010. I mean, that's what they were. We're not in 2010. You get the machine for free. It's better to get it than not have something. So, there's nothing really wrong with those specifications. You could do good treatments, but just know what else is out there and what other collaborations the companies are willing to do.
And after we finish the RFP, we send out maybe 2 or 3 company include the Patron. And maybe the next July, the beginning of July, we plan to visit Luitin Hospital. I think in the agreement, we will give us some idea how to what we need to explore, what information we need.
Yeah. So, and it depends which way you want to do it, right? So, if you're going down the RFP, I would get the information first, the written information, and then have them present. And this is you're getting to the point that you're like, we may sign a contract in 6 months, 9 months, right? Or at least start the negotiation. So before I go to do the site visit, I would go through this RFP process and say, get the information, learn as much as you can. And then part of that, when you're talking to say, okay, now we want to do a site visit. We want our accelerator physicists to spend a couple weeks just seeing within the treatment, not the treatment control, but within the accelerator control room, just so you get a sense of what's happening there, right? And you want either your medical physicist or your physician to spend a week or 2 weeks in the treatment control room, kind of just seeing them go through treating patients. And it sounded like they would probably be ready for the gantry in a couple months for them. I don't think you're interested in the fixed beam room or the half gantry, so I might wait till that gantry is ready so you can see the cone beam image quality and these different things. Kind of that timing, but and that gives you time to set the RFP, let them respond clear, and then have an actual in-person presentation to talk about each of these things, and be able to ask some more detailed questions. And then after that, then it's like, okay, you have 4 companies responded, and only 2 of them you want to go and see. And that way you can also see the difference. I mean, you can see the variant system here. They don't sell that system anymore, but you can see how it operates. And at least go see, another, let's say, a modern installation. And even if it's a carbon system, but thinking of, what would be the latest system to kind of go see that's not too far that you'd be able to build. Going to Singapore to see the Hitachi system, that's not too far, and you could go, and they're usually very collaborative, so you could go and spend time and kind of see and ask some questions. That way when you do go to the China system and you see that operating, you have a reference, right? Maybe it's operating pretty much the way the Hitachi system was. Whether there's this and then, okay, then it was the same. Or no, you really see some major issues or not. But unless you have something to compare against, it's hard. Because it doesn't operate like, none of the systems are going to operate like a Linac. Nothing's going to be that. Those things, you have a 10-minute patient slot, you just kind of go through and everything kind of seamless. No proton system is to that point yet. The IBA Proteus 1 is almost close, but not quite. So that's why it's just good to see, okay, this is a modern proton system. This is how it operates. Singapore does a good job. They, maybe they have 20-minute time slots. The Hitachi cone beam there is okay. It's not great, but you'll see that. That way, when you go and see the other system, you have a good comparison. the Sumitomo system, I mean, Korea is kind of far to go to, and it's like a 6.5 hour flight, so maybe not. Singapore might be the better one. But I started kind of doing that thing, but I don't think there's a rush to do that. I think getting the information first, kind of the written information, particularly since, you know, where we deal with the Japanese company or the Chinese company, you're communicating in English, and it's not the first language for either. So they're very easy for miscommunication to happen or a misunderstanding to happen. And that's why having it at the written documentation is important, because then, you know, they're able to interpret it and answer it in Chinese and then turn it. And then you have the meeting and say, is this really what you mean? You know, was there a mistrial? Am I misunderstanding this? And have clarifications.
This might not relate to the I just wonder that why variant stop their mistake. I think my question I just want to know that what factor that make the variant stop. So we have to learn is
I'll tell you, this is my understanding, right? So obviously I'm not inside the company, know all the details, but this is my understanding. They bought a company. The company was called Excel. So there was a company, Excel, it's a German company, and they were getting into proton business, but they never quite got there, right? They had a good accelerator, a good superconducting cyclotron, and that's pretty much all they had. So they never had all the things together, and they were kind of not really known. So they tried, and they just, that company Excel never kind of made a mark, but they did have a pretty good accelerator. Varian was never in the proton business. They started doing proton treatment planning because MD Anderson was going, and they were a big Varian size, so they needed to compete there. They wanted to keep the business. There was some decision made, hey, in Varian, we're going to get into the proton business. And they bought Excel. So they bought that company and all of their technology and IP. My understanding is from that one, there was never a good integration between the two companies there, right? You know how that always goes, culture and everything else. But with that aside, my understanding is Varian really wanted to kind of get rid of IBA. They saw IBA as the main competition. So Hitachi is always more bespoke, right? The Hitachi is generally a little more expensive, but if you want something to be a certain way, they'll do their best and they'll charge you for it to make it that way. So Varian really aggressively marketed and aggressively, so much so that they were basically not making any money off of their proton sales. So they were marking them down so they could compete, so that IBA wasn't selling any more systems. Now Varian was selling the system. So they weren't making any money off of them. And usually you make your money also off of your service contract, but they were pretty aggressive on their service contracts as well. And that led to some of the infighting with the Excel group and everything else, because they're the ones that were actually like receiving the service contract and having to maintain these things. So one, they were doing that, but they never actually got a huge market share. IBA was still selling systems and competing. So they're trying to undercut, never really kind of push IBA to the side. When Siemens bought them, and so Siemens acquired Varian. What I've heard through the people I know within there is Siemens looked and said, you're losing money on protons. And some companies did this, they call it a loss leader, right? We have this nice fancy proton thing, it's really cool and all this stuff, but they're not making any money off it, but they keep this good impression that they are the top of the line in radiation therapy and such. Siemens was kind of like, nah. And Siemens already has a history of, you know, cutting carbon therapy. They were doing carbon and they said, we're not making money, cut it out. They were doing Linux, right? Yeah. And their Linux are pretty decent. They had some issues here and there, but they weren't actually making as much money as their imaging. And it was just kind of thing. So eventually they just, so my understanding, Siemens looked at that and said, you know, you're not making any money off of this one. The only way you're going to make money, your price is going to go up, and there's no way you're going to be competing against IBA or even really competing against a Hitachi. So Siemens just said, no, we're no longer going to support losing money on this endeavor. So they just killed it. Yeah, so it's Varian still owns it. I mean, Varian owns the company, or Siemens does. Siemens owns the IP and everything. So yeah. Yeah, it's a good accelerator. It's a superconducting, so it's fairly compact. The other thing is they haven't actually spent any time improving it, and that was another kind of issue between the Excel group and the Variant group, right? Variant didn't put any money in kind of making it better or doing kind of. They spend their things more on undercutting the bids and kind of on the marketing and that side. So the base accelerator itself was pretty good. You know, it's a small footprint. The power consumption is pretty small. And they mentioned it when they said, you know, their power consumption is small compared to the old IBA system. You know, that wasn't superconducting. Now the IBA system is superconducting, and so is the Variant one. So superconducting, you don't use as much power and stuff. So yeah, so I think that was kind of the main thing that kind of happened on that. Is it, you know, it is hard to compete. IBA already had a decent market share and was in the field for a long time. And Hitachi has a really good product. You know, it's really stable. Synchrotrons have a lot of advantages. Cyclotrons have advantages that if you do it right, you can get a really high beam current. Like you can do flash really easy with the cyclotron. Synchrotrons are very hard. That's why like they're saying they're going to look at Linux or something, because the synchrotron is very hard to do real flash. For cells, okay, but anything else it's going to be hard to do with the synchrotron. But yeah, that's as far as my understanding.
I have a second question. This may not be made to our project, but if our project fail, I just want to know that what is your opinion about the single loop compact?
Like Mavion? So the Mavion product is okay. The spot size is pretty big. The dose rate is kind of low. So as a, you know, again, as a single room, if you're only going to put in one room and you want to be able to offer proton therapy, it's okay. I mean, it's still better than not doing it, you know. But yeah, their throughput's pretty low. Wash U in St. Louis, and they have like I think 3 of them, and they're you know, they still aren't treating that many patients through them. It's just kind of, so their imaging isn't very good. Like I said, I can tell when we used to do some, you know, when you do protocols like with the NRG or these things, you know, you have to send your plan off for sometimes to get evaluated. So I was on one of the groups to evaluate some of the proton plans, and I could always see when it came in, and it was, I could just tell that this was a Mavion system because the spot was big. I can just tell. I know it's not IBA, and I know it's not Hitachi. I can tell it's a Mavion system because, you know, you don't have a good penumbra. Yeah. So, I mean, it's better than not having anything. But, and then again, once you go for 2 rooms, then the cost and everything else becomes like, it's not really that. If you're only doing 1 room, then it's competitive. But that I'd rather do like a IBA Proteus 1 or something. Yeah, B-Down Medical. Yeah. There was a reason I did not put them in when I did the list of things. Yeah. So the concept, the core concept is pretty interesting. Everything else around is just weird. You know, once you go the patient on a gurney that's going to go like this, and they really, where's your imaging? Have you ever? So at Mayo Clinic Rochester, Arizona, we tried the thing because it sounds really good. We had these setup rooms that you can set up and then bring the patient. We had the robot with the camera to get them in, and it never worked. It just didn't. You're moving the patient. You know this, when you do a couch kick, the patient moves. You know, no matter how it just does. Rolling it, it's just like, you know, their gantry, even the way they designed the gantry, there's things that could have been better. But the concept and the one in charge, he's very smart. He actually is the one that designed the nozzle to Toshiba, so he knows what he's doing. But in that realm, but he doesn't have the clinical portion in there. And just you look at it like, no one's gonna do. It's not gonna happen. You know, so that's good. I didn't even include him in the list. But actually, Toshiba is trying to right now, because a lot of people say, I want protons and I want carbon. Toshiba doesn't have, so Toshiba is trying to say, maybe we could do something with B.Dot Medical to be the proton portion. But the two institutions that I have looked at, they both said, like, this is just weird. I don't know what you're doing. So that core technology is interesting, but everything else is just, yeah. But it's a good group, you know, and they're trying. They don't have a system yet in Japan. They're negotiating, but no one's actually kind of bought into it yet. But yeah, if you decide to go one room system, I would probably say just go with IBA. You know, they have a good system, it works, their imaging is pretty good, and you know, there's a lot of them out there, and it'll be fine. The Hitachi one room system is a little bit big. I don't know. That actually system is pretty good too. They have a couple of those ones in also. But I would kind of, if you did go down that path, I'd kind of stick with those ones.
Do you think one day proton will be standard treatment like the photon or not? Because we need to make this decision. Is it bright future for us or not?
Yeah, well, personally, I think so. I mean, well, even when you went from 3D to IMRT, right? You could look and you know it's better. It's better for the patients. But there's no clinical trial you can really do that can effectively kind of show that this is notably better, right? I mean, some of those, just the doses more conformal, the less dose to the normal tissue. You got to do a long trial follow-up. You know, it's just not going to happen. And I think that's just basically with attrition is what's happening with protons. Right now, proton is done basically as I'm going to say as a replacement for proton. You're giving the same dose to the tumor, and what you're doing, you're sparing normal tissues. Okay. So when you do a trial that says, do I have better tumor control? No, you're giving the same dose, you're going to have same tumor control. You do see, like for head and neck, there's some things, your side effects, your acute things are lower, but you're not going to show that you have better tumor control until you start doing trials where you're saying, this is, and there is a liberal trial out there that's saying, this is the max dose to the liver, but I'm going to give as much as I can to the tumor. And the constraint is going to be my liver constraint. And protons, you're able to go way up there, right? And photons, you can't. So I think once some of the thought process has changed to like, okay, what we're really going to do is for these ones that the tumor control probability is not that great, I'm going to start intensifying the treatment, maybe do more SBRTs, these kind of things, to give more dose to the tumor. But now my normal tissue is going to get the same. Maybe I have the same complication. I have the same complication rate, but now I'm getting better cure. And I think those are the things that are kind of happening now. So just because it is more expensive, I think it's slowly going. But anytime you see, you know, these plans compared, you're like, if I'm getting the treatment, I want this. So I do think that the future is going to get just more and more as the costs come down. I mean, I didn't show, you know, the one I can say with the development one that really is going to be able to fit into one room, and we're trying to really get the cost low. So I think eventually you're going to start seeing, you know, probably in the next 5 to 7 years, like the B.Dot Medical, I think the other one we have is a little bit better, that it really is starting to get a lot smaller and a lot less expensive. But again, maybe that's going to happen and you put one of these in 4 years, or maybe it's going to take longer and it's 10 years. And if you have the opportunity now, you know, this system that's going to go in is going to do just as good. So that's kind of my biggest take home from this is that their system is fine. They have a lot of learning to do to make it better. But if you're to put that system in the way they have it today, maybe a little bit of improvements here and there, and they have a decent cone beam, you're going to do good treatments. You know, you'll be able to do really good treatments. The patients will have the benefit from it. So it's just really, you know, weighing the different things. Maybe one might be a little bit better, and if they're able to give you a good agreements and stuff, maybe then you want to go with an IBA. But this system, I think, is okay. So yeah, really the next step is what do you want to do next?
Last time, maybe,
20 minutes. 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 20
Like a chair solution. So that's the one I showed. So maybe on they call it the Fit, and the one the Israeli company Peak here, I think. So I showed a couple of those ones. I can't remember. They all of them have like similar thing. Like Hitachi calls their thing the Pro Beat. I'm like, can you come up with something else? Everything sounds the same. But yeah, so people are now looking at I could have this and I could do things on a chair. For the first system like this, it's risky. No one's really treated like all your patients. This is now you have proton therapy. You can treat all your patients this way. How does it work with head and neck? How does it work with breast? Anatomy wise, what's happening here? Then you have to CT them in this position, right? The CT scanners that they have when you have this, it really isn't that good, right? And can you actually do that CT? If you get treat prostate or you get treat pancreas, you get treat here. Are they actually standing? Can they actually stand long, even though they're supported? There's a lot of things that we know very well when the patient's laying on the table. Yes, there are some patients that is very uncomfortable, right? Some of the ones with head and neck or other things are, in the back, it's hard. But a good majority of the patients are able to tolerate. There's only a few patients that are really like, I can't lay down. And then you sit them up a little bit, do different kind of things. So I think when it starts looking at that and trying to treat all these patients and everything like that, you're going to find, my guess is you're going to find that it's good for some, but it's not good for all the patients. And then it's going to be more of a niche, maybe a few types of things you're going to be able to do. But again, that's just right now the way I see it. And maybe again in 5 or 10 years that a lot of people have started doing this, you solve the problems and you're able to do it for most patients. I wouldn't want to be one of the. And usually I'm fine kind of taking some of these risks and doing, but that's more. The patients themselves, right? Like CTing the patient this way, treating the patient this way, image guidance, so you do the CT and then you do the image guidance. Now you're rotating the patient. Yeah. So they, you pose the patient, they set up something like this, and then the CT comes and this, from the top and goes down, and again, then you need your treatment room is now your sim room. So how many patients are you actually going to treat through there? There's a lot of questions on that one. And again, it may be solved. And again, 10 years from now, that may be like, okay, this is the way we really make it small. But I mean, radiation therapy started with a chair, right? And I found really quickly that a gantry so a chair solution for a LINAC is better. That's been existing for a long time. So people have found that this other way is better.
Is this machine from last year?
Huh?
Is this machine from last year? Is this quite similar to the machine from last year?
Yeah, so Proton, so those is the one that I showed. So there's so Proton has their synchrotron. They have serious supply chain issues, mainly because their synchrotron comes from Russia. So they haven't been able to do a thing. And their group, they actually tried to do a Proton system in Michigan many years ago, and they finally got it working. So that group has had issues for a long time. They put one into Massachusetts General Hospital, and it's working. And honestly, the people there hate it. It functions, but it's not very good. So it is a system that exists. I would not send them an RFP because I just know their system and the people that have worked with it. It wouldn't be something that I would recommend. Hey, look into this. And again, that was the one in Adelaide in Australia. That's the one they put in. They haven't had any equipment. They have the building already, but no equipment has shown up. And there's a lot of problems. So I think that company is basically going to go bankrupt and stuff. So I don't know.
So what time did that be, did the company say?
I would send the, let's say, the traditional RFP to IBA, Hitachi, and Sumitomo. And then do a special RFP to Afton, right? There's special more, again, because there's a relationship of asking the questions, what is your thing, as opposed to saying, you know, this is what we would expect. And no, and Hitachi's gonna say, we can't do that, we can do this. And they're used to doing that. I don't think they've ever got an RFP, and, you know, it might be, I'm just saying the relationship wise, it's, and I picked up yesterday or something that there was a little bit of even them being iffy about you going and spending time and looking at their things. I don't know. I picked up that maybe there was a little bit of sensitivity. So I think you can be careful about that. You could get the same information and by just asking the question. It's a little more work on you to pose the question properly instead of saying, you know, I expect a fill size of this and I expect this dose rate. You know, you could just say, what would be your dose rate for this volume like we demonstrated? What would it be for this volume, kind of things? And they should be able to answer those. I mean, they have a system working. They could just make a plan and try it out and measure it. I guess selfishly, a next step would be, when would be the next time we would do an in-person thing? And I know it's going to be virtually impossible to go to Shanghai, so I think we already had decided we would do 3 here in Bangkok, and hopefully maybe they'll come and present or something. So, like for the next one, how would you like that to do? Are we thinking of trying to do something this summer? You know, I have proposed that maybe right after PT Cog I could, you know, come here, but June didn't work out for you guys, which is totally fine. So do we want to try to figure out a July timeframe, and maybe on the timeline we would have their responses, then we could meet and go through their responses and things like that, or
next week, after we get our interview response from
that, yeah. So it again depends how kind of the timeline. So when I think when we first talked, or now, it seems like ideally negotiations would start at the end of the year. Yeah, you know, they'll take longer, but or maybe it's next year. I don't know. There was originally like phase 0 was gonna stop at the end of this year, and phase 1 was gonna start next year. Maybe they extended. So I'm not too sure exactly, you know, what stage you guys are at. And if it was to the point that, okay, we want to, you know, have a preferred vendor, you know, you have really seriously looked at them, really asked questions, and you're like, okay, you know, the Chinese company we're going to go forward and talk more about them, because they still look reasonable. There's nothing out, you know, their machine looks fine and stuff like that. If we want to get to that point, like in the thing, I would think we would need their responses to come in this summer, like their written responses, and maybe even their presentation, you know, I put in there in August or something. So that's kind of the question. If they've already told you, well, no, we actually, you know, the timeline is really, this phase 0 is going to go till the middle of 2025, or, you know, so it's more really, I don't know exactly what your timeline is looking like. So it's really.
Submitting report end of this year.
Yeah, that's another one. Okay, so at the end of the year, you want to do a feasibility report, right? You want to do your due diligence. So, the way I interpret that is you want to be able to present and say, this is what Apton has, right? This is what a Hitachi system would be, or a Sumitomo system would be. These are the pluses and minuses. Like they have this thing. Look at them really and judge them. And usually there's a criteria, you know, come out and put this thing and say, look, this one can do this, and some things can do other things, and not even worrying about the cost right now, right? One thing you would ask him is how much it would be in the RFP. You want to know, but you'll leave that to negotiation. There'll be a thing, you know, this is how much they say, but you do your evaluation, say, here's pluses and minuses of the companies that were willing to say that they're willing to go and install a system here. And that's kind of that RFP process, right? You get this, and that maybe you don't get to the point that you do a letter of intent or memorandum of understanding, but you're getting all this information so you can write this report. So then the ones that would negotiate or do these things, they could look at it and say, okay, you know, actually, again, IBAs look really, really good. They want to come in. Maybe they are willing to do some things with, you know, with your group and say, you know, make things or whatever it is, right? And there's that thing, and we have that collaboration. I don't know, maybe with Sumitomo or with Hitachi, with the Japanese company, they're willing to do these things. They want to come into Thailand and do these things and compete and do, you know, because I'm guessing you haven't really talked to them, right? And particularly if this gets to more of a governmental level, you know, then maybe there is something. Maybe the Japanese government with the Thai will do something for technology transfer and everything else. You know, so it's that thing, just to really see what they're willing to do at what stage. And that way you then have the information, and the other people then can then talk to, you know, whatever your Minister of Energy or Healthcare may talk to the Japanese one and say, hey, is there something here? I know they've talked to the Chinese one, but maybe there is something. Maybe they're willing to do something. But the first thing on your part, and the part I'm helping on, is to look at this and say, on the technology wise, and again, at first pass, their thing looks fine. They're at where Hitachi was 15 years ago. They will probably learn faster just because it's already been done, so they know it can be done. Hard part is to even, can we actually do multi-energy extraction of protons? If you talk to the Europeans, they always said they couldn't do it because they couldn't solve it. So PSI, you know, really smart people, but they could not solve multi-energy extraction with protons. So they go to PT College. They even 2 years or in 2019 before COVID, they said you can't do multi-energy extraction with protons. And I got up and said, that's not true. We're doing it. And then he still presents that and says, now he says it's really, really hard to do it and no one actually really does it. And I say, no, we do it. So part of it is just to show it can be done. And now they know it can be done. So, you know, they can work towards it. So they'll probably ramp up faster than Hitachi. Hitachi had to do it for the first time. So they know it can be done. They could learn some things and be able to do it a little bit faster. But that, again, that's that initial impression. Until we get detailed information, kind of that really nitty-gritty stuff, you know, and there's other things about delayed charge and how it's, you know, all these other things, how their control system actually works, that will really know how much effort they put in.
And also it's safety or not complete.
Yeah. Yeah, and that's some of those, like, you know, and they said they complied with the, you know, the ISO standard, the IEC standard of these things. And those are the basic, but it's easy to say you comply. And some of those compliances aren't really the true safety, like you're thinking of safety, like, you know, the dose actually stopping. It's that they did things in a certain way. Like for software, when you design software, you have to design it in a certain way. And some of those are just the compliances. At the end of the day, still you really have to check. That's why you check, you know, the monitor cameras, does it actually stop when it says it stop? Does it actually stop as fast as it says it stop? The gantry goes and you hit the emergency stop. Does it go, or does it actually stop, right? You know, that you actually see that, and maybe when you go in person, you say, hey, and on the weekend or something, can I see your emergency stop? And if they're not willing to do it, I mean, one, maybe they're not confident, or two, the recovery takes so long they don't want to do it. But that tells you that they give you information, right? They're not willing to do it, but you go to Singapore with a Hitachi machine, and then yeah, on the weekend we'll go ahead and we'll hit an emergency stop, and you can see what happens and how you recover. So I'm just actually being selfish to kind of plan out my summer, like when the next time I would come here. Really, that was really the next step, is to see what would be the next thing.
When we go to China, should we tell them to make sure that they close or
Some of those, not, I wouldn't really. I mean, I would go during, you know, they have that 2 hours of morning QA. So when I go do a site visit, I spend like all day there because that's what you're there for, right? Well, what are they measuring? If they're spending 2.5 hours doing stuff, I'm guessing they're measuring some death doses and different things. I wouldn't do anything such like that because the energy coming out is going to be the energy. I don't have a worry that they're getting big changes or anything like that. It really is more on the accelerator side to see back there, like, are they really kind of having to tune things all the time? Like it's really there and they're really involved, or is the engineer is like just sitting there watching the thing but doesn't really have to do anything, right? The system is actually working, or are they constantly fiddling with stuff? That tells you a lot of information. And on the clinical side, the treatment control room, what are they doing? Yeah, it's like, load this, do this, press this button, press this thing here, do all this stuff before they treat a patient. It's like, that's really complicated. The likelihood for an error happens, go higher. Whereas they're really smooth. You load it up, they do the imaging, they treat, right? Are they having to do a lot of ignoring warnings, or, what is that? What is that happening? Oh yeah, yeah. I think you have to observe for, I would say 2 weeks. Maybe they won't let you for 2 weeks.
Yes, we have a process. Only 2 days. But you 2 days. What you don't do it. The first phase,
Yeah.
and you can first say, form together after they commissioning
The gantry.
The gantry already.
Yeah. Yeah. I mean, I'll just, if it's the half gantry, I'll just be in the control room from 7 a.m. till they're done. And we're done with QA, right? Just see what they're doing. How, is it a pain in the butt to work with this machine? Because that you'll have to live with that every day. And I could guarantee from whatever they have there, and if you're gonna put in the system, that part's not gonna change much. They'll tune some things, little things here and there, but fundamentally, they didn't say in the roadmap that fundamentally they're gonna change their interface or anything like that, right? They even said it's already in English there, you're gonna get the same interface. So you want to know, like, well, what are your therapists gonna be doing every day? Is it just hard to work with? And like the first Hitachi machine, like the MD Anderson one, it was painful to do. I mean, there was like, you got to press this button, you got to do this, you got to load this, you got to do this. It was like a jigsaw puzzle, all these things that you had to do just to get it ready. And the likelihood of error was high. Now their system is, very straightforward. Those things don't exist anymore. It's almost, their new system is, we'll see if they do it right, it's almost going to be like the TrueBeam. The IBA system is very easy to work with. It's very straightforward. The imaging is very straightforward, these kind of things. But the more complex it is, and if you're comparing apples to apples, right? If they're giving you the system for free, you take it, right? Okay, we're gonna get it. You're still gonna treat patients good. But if you really are comparing it like to the Hitachi machine, you want to see this to say, this is going to be really hard to work with. I'm not going to be able to treat in a 15 or 20 minutes time slot. It's going to take 30, 40 minutes for every single patient to go through. So that's what you want to feel. It's not any specific thing of like, oh, the depth is slightly, or, the beam position is this, you're not going to learn that, but you're going to learn, or you're going to learn that, a fault, it aborts. Why is it aborting so many times? What's happening? Yeah. I think your job in that part is more straightforward, right? Because in that, but it's not their planning system, right? It's race station.
Yeah.
So yeah, that's all. At this stage, it's really, I mean, you might want to just see the patient experience, right? Again, to just go and see, like, the patient's on the table for 45 minutes for a brain treatment. That shouldn't happen, right? 3 fills, it should have been 20 minutes, but it's taking forever. You want to see what your patients are going to go through. But the medical physicist or a therapist that go can give you that kind of information. But yeah, the treatment planning system, they use race stations, so it has nothing to do with their machine, right? The plan quality isn't, their spot size is a good spot size. So the plans are going to be fine. So you're not really going to learn anything there on that portion of it. You can go anywhere and see those kind of planning being done. But for the radiation oncologist, I think the important part is is that patient experience. What is your patient going to actually be going through, right? As opposed, if you go see a Hitachi machine and, you know, they do a brain treatment, a 3-field brain treatment, and it takes 15 minutes with imaging and everything, or 20 minutes. Okay. In this system, it took him 45 minutes. Well, that's 45 minutes that you have them, I don't know, maybe you have worn the mask. I've done the thing. After 30 minutes, I'm like, oh my God, I got to get this thing off of me. You know, so, you know, that's kind of that kind of a feel.
Also, like, patient will see patient will approach with process. How much time do we
Like,
you have to observe that how they go to the patient, right? To it be only 1 week or
yeah, so that patient experience. And that's why right now I wouldn't, until they have the full gantry at cone beam and see that image quality. Right now, they just have the radiographic imaging. That's why it's like, when they have the gantry and they've been training a little bit, then because that's what you're going to be putting in, right? So you want to see that experience. I mean,
that have they shown the certificate right? And we have probably possible.
yeah, like if they are commissioning it, like you could then see some of the cone beam with the phantoms. But as you know, with the phantom is one thing. A patient, it always looks a little bit different. But as far as on the physician part, those would be the things I would think you'd be interested in. What is your patient going through, and how good is the imaging? Because you have to review the imaging, right? You're going to sign off and review the imaging, and this is like, this cone beam is awful. I can't even tell what I'm looking at. And you go to an IBA system, you're like, hey, you know, this looks like the true beam. I know what's happening. Then you're able to kind of judge those things. And sometimes you can improve the cone beam by software, but if they're fundamental hardware, like, you know, you need the bow tie filters. Like, if they don't have a good design, and they say they're building most of it in house, most of it has been published, so they should be able to do this. But you know, it's their first time putting it together. Maybe they don't do a really good job, and it doesn't look good. And no amount of software manipulation is going to fundamentally change how good. They're probably going to buy the X-ray source from. They're probably not going to buy the X-ray tube or the panel. They're not making those themselves. They're buying it from somebody. And it's probably the same. You know, there is variant makes most of them, but I don't know. But there's probably a Chinese company that also makes them, so they're probably getting it from there. So I don't know if there's like a Chinese Linac vendor. Sure there is. So maybe they're just getting that cone beam hardware from that. So, you know, those things, I think they'll be able to do a good job. Their first one's going to be okay, and they'll make it better. But it really is fundamentally that system. Like the Hitachi first system at MD Anderson, it just took a long time to do everything. Like, and it was painful. But that was in 2025. You know, that was 20 years ago. Yeah. Yeah, you just stay a little bit longer at PT Cog, and you know, park is nice, and you know, you just go there even at the weekends. They have probably like the 2 generations back, but the system they have is pretty good. They have, I don't remember, their cone beam is different because I think they come out of the wall. So Hitachi does, every single system is different. So their imaging, I think, comes out from the back wall, as opposed to their new system, like the one they just put into MD Anderson, put in a new Hitachi system that has the imaging panel on the nozzle. So it's hanging in this there, so you could always image it, do something, and the things don't have to come in and out. So some things like that are a little bit different. Like if you were to get the Hitachi system, you probably wouldn't get this version. But you know, it's the same panels. They have roughly the same source to imager distance, so the image quality be about the same. And you'll be able to see the workflow, like, and that is the old Hitachi workflow. They're putting two systems into China now, carbon proton system. And then the system they'll put in for us, and the system they're going to put in Minnesota, the Rochester's putting in another system. That would be, the whole interface is totally new. So if you were to go with Hitachi, you would probably get that new interface. Like if you decided you did all this thing and for whatever reason, okay, you decide Hitachi's the system you're going to go with, you'll actually have a new interface. Yeah. Well, that's actually, I was thinking of coming here, right? That's the come I asked at that time. It's right there. I was like, I'll be over my jet lag if you just come. I'm right over here. But yeah, you guys said June was, there's a lot of things happening in June.
Maybe can open it for doing the.
Yeah.
Next month.
Probably not. Yeah.
Maybe take thatที่เมื่อก่อนเราไปจีนหรืออะไรไปจีนแล้วเราเชิญบริษัทมาเราไปเช่าโรงแรมมีขนาดใหญ่เราไปเช่าแต่ว่าเขาไม่ได้ไม่ได้เขาโอเคโอเคเนี่ยเพราะว่าเราที่เราแบบได้เวลาเราพวกมือแน่นสุดด้วยแต่เราสามารถเซตออนไลน์เขาได้เราเซตออนไลน์เขาได้มีเอเพื่อนอะไรต่าง
So there's a group of you going to PT Cog. I guess this is pretty close, right? But so it'd be hard to send an RFP and get responses back because they're, this is the big conference for them, right? So they're going to be putting a lot of effort into getting ready for PT Cog and their booths and stuff. But what might be worthwhile is before you go to PT Cog to contact Sumitomo Hitachi, IBA, and anybody else, and say that you're really interested, your hospital is starting to look at this, and you have a pathway that probably within the next year you're going to be moving forward, and you want to just talk with them there. So that way you can meet the people and see, okay, these are the people I'd interact with. This is who will probably come to present. You could ask them, who should we're getting ready after PT Cog, we're going to be sending out requests for proposals, or we're going to be sending out our information gathering. You don't even have to call it request proposal. You're going to send out different companies your information gathering. Who should they be contacting and these kind of things, and kind of start those discussions a little bit, just to kind of, and I would, most of them, you probably know the people, and if not, I could probably at least get you a few names that you could kind of contact and say, you're interested, that you want to just talk with them there and start discussing, just as a first step. So yeah. Yeah. But then you're kind of talking to the middleman. And I would just talk to them, and then for whatever relationship, maybe then they have to go through this thing. But so this is what I know from Korea, working on those and kind of helping him with things. And it may be the same here. So if you buy a variant Linac in Korea, you actually pay a lot more than we do in the U.S. because the middleman makes a 50% profit off there. So, it's kind of, so for these things that are, and sometimes even buying a water tank, I was actually surprised that buying the water tank actually costs more I thought they would charge us more. You know, it's the US. I thought they were going to charge us more, but it was actually cost more in Asia to get it because it's not IBA or PTW that sells it. It's this other company that represents them, and they get the same. You know, they buy it for the price that I pay for it, and then they charge an extra 25%. So they make. So I will try to cut out that person, and maybe, you know, for whatever reason they can't. But for this type of a project, I would go straight to the source. I would.
ก็พวกไว้ค่ะเอาคุณทำให้ดูเรื่องแล้วเอาไปได้เล็กๆนะที่ไปต่อยไปที่แบบได้ครับไม่ใช่แบบไปเรื่อยๆแบบปรับความเกิดขึ้นในประเทศไทยแล้วไม่ต่อเราไปเจอที่ของเดี๋ยวเราลองให้เป็นทีมที่ดูแลบทบาทออกเพราะเราลามไปเป็นในการคิวเป็นดิวเลยก็จะมันก็จะชวนเลยเป็นที่เลยมันเป็นงานใหญ่เรามีเวลาในการเตรียมแล้วก็ส่งให้เขาดิวเป็นรอก็คือไปถึงให้ส่งตรงใช่ไหมพีเอน่าจะตอบเอนะจะให้พีเอน่าจะไม่คือเขาคือแรกเข้าใจว่าเขาไม่อยากให้ส่งตรงเนี่ยถ้าเราจะส่งพีเอเขาทำก็คือเขาแต่ว่าแล้วก็อีกPBI ก็อีกที่เขาเป็นไงเนี่ยไทยก็มีคนแชร์พี่คิดว่าอาจจะไม่ได้เป็นวัยตัวแทนที่ใครคือถ้ามองตอนนี้นะไม่เป็นสุดท้ายเราก็เจรจาอยู่ดีไม่แน่นะติมีเพื่อนพิตาชิมามีต่อไหมเขารออยู่เราจะยังไงต่อ thank you อะไรคอมเมนต์มาก็ใส่เราวิธีชอบเดี๋ยวเราแบบที่เราคุยเราFor that, I'm going to send it out to also watch it. Thank you.